This is the beginning of the most ambitious journey you will ever take. Over the course of this series, we will explore the complete story of our solar system. Every world, every moon, every asteroid, and every particle of dust that orbits within the sun's gravitational domain will be laid bare before you. We will descend through the sulfuric acid clouds of Venus and walk across the frozen nitrogen plains of Pluto. We will dive into the liquid methane seas of Titan and witness the diamond rain storms that fall through the crushing depths of Neptune's atmosphere. We will stand on the red deserts of Mars, where ancient rivers once flowed, and investigate the volcanic fury of Io, the most tortured moon in the entire solar system. We will explore the rings of Saturn, where billions of ice particles orbit in perfect synchrony, and venture into the asteroid belt, where the shattered remnants of a planet that never was still drift in eternal silence. Before we can understand any of those worlds, we must first understand the God that rules them all. Every drop of rain that has ever fallen on Earth, every gust of wind that has ever carved a canyon on Mars, every storm that has ever raged across the face of Jupiter, and every flicker of light that has ever danced in the auroras of Saturn, all of it is powered by a single terrifying object. That object is the sun. It is the king, the tyrant, the giver of life, and the harbinger of death. It is the anchor that holds our entire cosmic neighborhood together. Without it, the planets would scatter into the void like leaves in a hurricane. With it, we are prisoners, locked in orbits dictated by its immense gravity, bathed in its light, and ultimately doomed by its evolution. To the average person, the sun is nothing more than a pleasant yellow circle in the sky. It rises in the morning, bringing warmth and light. It sets in the evening, painting the horizon in shades of orange and red. We build our lives around it. We complain when clouds obscure it. We paint it on children's drawings with a smiling face and cheerful rays. We take it for granted as a benign, unchanging lamp that hangs 93 million miles away in the blackness of space, illuminating our world with a gentle, steady glow. This perception is the greatest and most dangerous illusion in human history. The sun is not a lamp, it is not gentle, it is not smiling, and it is certainly not benign. The object that dominates our daytime sky is a raging, screaming inferno of nuclear violence. It is a continuous explosion of incomprehensible scale, held back from annihilating itself only by the crushing weight of its own gravity. If you could strip away the vacuum of space, the only barrier protecting you from the acoustic reality of the cosmos, and replace the emptiness between Earth and the sun with normal atmosphere, the sound would kill you, not metaphorically, literally. The sun is not silent, it roars. Deep beneath its surface, convection cells the size of continents rise and fall, each one carrying the energy of a billion atomic bombs. The plasma crashes down at supersonic speeds, slamming into itself with the force of planetary collisions. The magnetic field lines twist, snap, and reconnect, releasing shockwaves that propagate through the star's atmosphere at thousands of miles per second. If sound could travel through the vacuum, the noise would be overwhelming. Calculations suggest that the sun would register at around 100 to 125 decibels at Earth's surface, roughly equivalent to standing next to a freight train horn blowing continuously, day and night, forever. At that volume, conversation would be impossible. Sleep would be impossible. The sound would be physically painful, a relentless assault that would drive every living creature to madness within hours. We are spared this auditory nightmare only by the silence of space, but we are not spared the violence itself. The sun is attacking us right now, at this very moment, with a fury that would make nuclear warfare look quaint. To truly understand what we are dealing with, you must look at the numbers, and the numbers are absolutely horrifying. Deep in the core of the sun, where the temperature reaches 15 million degrees Celsius and the pressure is 260 billion times the atmospheric pressure at Earth's surface, hydrogen atoms are being crushed together in a process called nuclear fusion. Every single second of every single day, the sun consumes 600 million tons of hydrogen fuel. It forces these atoms to merge, forming 596 million tons of helium. The math doesn't quite add up, does it? 4 million tons of matter vanish every second. Where does it go? It doesn't go anywhere. It is converted directly into pure energy in accordance with Einstein's most famous equation, E equals mc². 4 million tons of mass, the equivalent of a mountain range, is vaporized and released as light, heat, and radiation every single second. To put this in perspective, the atomic bomb dropped on Hiroshima in 1945 converted roughly 700 milligrams of matter into energy. That's less than the weight of a dollar bill. That minuscule amount of annihilated mass was enough to level an entire city and kill over 100,000 people in an instant. Now scale that up. The sun is converting 4 million tons into energy every second. That is the equivalent of detonating 10 billion hydrogen bombs every second, not over the course of a day, not over the course of an hour, every single second. Imagine every square mile of Earth's surface covered in nuclear warheads, all detonating simultaneously. Now imagine that happening again a second later, and again, without pause, for 4.6 billion years. That is the object you are orbiting right now. We exist only because this apocalyptic explosion is perfectly contained. The sun is trapped in a state that astrophysicists call hydrostatic equilibrium, a delicate and terrifying balance between two competing forces that are locked in an eternal war. On one side of this war is gravity. The sun contains 99.86% of all the mass in the solar system. It is 333,000 times more massive than Earth. That enormous bulk generates a gravitational field of crushing, incomprehensible intensity. Gravity has only one goal: to pull everything toward the center. It wants to collapse the sun into a dense cinder, a white dwarf, or if the star were heavier, into a neutron star or a black hole. The force of this inward crush creates pressures in the core that are beyond anything we can replicate in a laboratory. We are talking about 265 billion atmospheres, pressures so high that the normal rules of chemistry break down entirely. Fighting back against this gravitational collapse is the outward pressure generated by the nuclear inferno. The photons, the particles of light, created by fusion in the core, are slamming into the overlying layers of plasma, pushing them outward with immense force. The sun is held up, quite literally, by its own light. It is a balloon inflated not by air, but by the explosive fury of thermonuclear reactions. If the fusion reactions were to stop, if the core were to somehow run out of fuel or the conditions changed just slightly, the outward pressure would vanish in seconds. The sun would then collapse inward under its own weight, shrinking catastrophically in a matter of minutes. Conversely, if gravity were to weaken, the sun would explode outward, blowing itself apart in a cataclysmic detonation. But neither happens. For 4.6 billion years, these two forces have been locked in a perfect stalemate, balanced to within a fraction of a percent. We live in the neutral zone of this cosmic battlefield, basking in the waste heat of a war that has raged since the dawn of the solar system. But here is where the story gets even stranger. The energy produced in the core does not escape instantly. The core of the sun is not a hollow cavity where fusion reactions take place in open space. It is a seething mass of plasma so dense that it makes solid lead look like a thin gas. The density at the center is about 150 grams per cubic, times denser than water. In this environment, a photon born from a fusion reaction cannot simply fly away. It gets absorbed almost immediately by a nearby electron or proton, then re-emitted in a random direction. This begins what scientists call the random walk. The photon moves a tiny fraction of a millimeter, then collides with another particle. It is absorbed, it is re-emitted, it bounces left, then right, then downward back toward the core, then upward again. It is a drunkard stumbling through an impossibly crowded room, trying to find the exit. This chaotic pinball game happens trillions upon trillions of times. The photon is not traveling in a straight line. It is meandering, lost in a maze of matter. As a result, a photon created in the core of the sun can take anywhere from 100,000 to 170,000 years to fight its way to the surface. Think about that for a moment. The sunlight that touched your skin this morning, the light that warmed your face and illuminated the world around you, was not created this morning. It wasn't created yesterday. It wasn't created last year or even last century. It began its journey when early humans were just learning to make stone tools. When that photon was born, Neanderthals were still hunting mammoths in Ice Age Europe. While humanity discovered fire, built the pyramids, invented writing, fought the Roman wars, sailed the oceans, split the atom, and landed on the moon, that photon was still trapped inside the sun, slowly fighting its way out. It only reached the surface about 8 minutes ago, finally free to race across the vacuum at the speed of light and strike your retina. We are looking at ancient light. Every beam of sunlight is a time traveler, carrying energy that was forged in the depths of nuclear fire tens of thousands of years ago. This incredible delay also means that the sun is hiding a secret from us. If the fusion reactions in the core were to suddenly stop today, if some unknown mechanism shut down the nuclear engine, we wouldn't know for thousands of years. The surface would continue to glow, powered by the fossil energy slowly leaking out from the interior like heat escaping from a dying ember. We could be orbiting a dead star, completely unaware that the heart had stopped beating, until the very last photon finally crawled to the surface and the lights went out forever. But the sun is not just a static ball of light and heat. It is a dynamic, churning beast alive with magnetic fury. Because the sun is made of plasma, ionized gas composed of free electrons and protons, its rotation generates a powerful magnetic field. But unlike Earth, which rotates as a solid body, the sun rotates differentially. The equator spins faster than the poles, completing a full rotation in about 25 days, while the polar regions take closer to 35 days. This uneven rotation drags and twists the magnetic field lines like rubber bands being wound tighter and tighter. Over time, these field lines become knotted, tangled, and stressed. When they finally snap, they release energy in the form of solar flares and coronal mass ejections, eruptions so powerful that they make the continuous fusion in the core look almost tame by comparison. A single large solar flare can release as much energy as millions of volcanic eruptions happening simultaneously. These eruptions hurl clouds of plasma, each one the size of Earth or larger, into space at speeds exceeding 2,000 miles per second. When one of these plasma clouds slams into Earth's magnetic field, the results can be devastating. In 1859, one such event, now known as the Carrington event, struck our planet. The geomagnetic storm was so intense that telegraph systems across Europe and North America went haywire. Wires sparked and caught fire. Telegraph operators received electric shocks through their equipment. Auroras, typically confined to the polar regions, were seen as far south as Cuba and Hawaii. The sky over the Rocky Mountains glowed so brightly in the middle of the night that miners woke up and started making breakfast, convinced that dawn had arrived. If a Carrington-level event hit Earth today, the consequences would be apocalyptic. Our modern civilization is built on a foundation of electrical grids, satellites, and digital infrastructure, all of which are exquisitely vulnerable to the sun's magnetic fury. A direct hit from a major coronal mass ejection would induce powerful electrical currents in power lines, melting transformers and plunging entire continents into darkness. The giant transformers that form the backbone of the grid take months or even years to manufacture and replace, and they can only be built in factories that require electricity to operate. A severe solar storm could knock out power for years, crippling everything from water treatment plants to hospitals to communication networks. The internet would collapse, GPS satellites would fail, the global economy would grind to a halt. We have built a fragile house of silicon and copper on the rim of a volcano, and we are long overdue for an eruption. And yet, despite all this violence, the sun is the only reason we exist. It is the ultimate giver of life. Every calorie of energy you have ever consumed, whether from a plant or an animal, ultimately came from the sun. Photosynthesis captures sunlight and converts it into chemical energy, fueling the entire biosphere. The oxygen in the air, the water in the oceans, the warmth of the climate, all of it depends on the sun's steady output. We are children of the star, built from its light and destined to die when its light changes. Because the sun is not immortal, it is dying. Every second of fusion consumes fuel that can never be replaced. The sun has already burned through roughly half of the hydrogen in its core. As the fuel is consumed, the core shrinks and grows hotter. This causes the sun to slowly increase in brightness. Right now, the sun is about 30% brighter than it was when it first formed 4.6 billion years ago. In another billion years, it will be about 10% brighter than it is today. That might not sound like much, but for a planet like Earth, perched precariously in the narrow habitable zone, It is a death sentence. The increased solar output will trigger a runaway greenhouse effect. The oceans will begin to evaporate. Water vapor, a potent greenhouse gas, will trap more heat, causing more evaporation in a vicious cycle. Within a few 100 million years, Earth will resemble Venus, a baked, lifeless hellscape with surface temperatures hot enough to melt lead. The biosphere will be sterilized long before the sun becomes a red giant. This is the sun's inevitable trajectory: birth in violence, life as a controlled explosion, and death as a bloated, dying ember that will consume the inner planets and leave behind only a cold, crystalline corpse. But to understand this ending, we must first understand the beginning. The sun was not always here. 4.5 billion years ago, the space where you are sitting right now was filled not with light, but with darkness. The solar system did not exist. In its place was only a cold, silent cloud of gas drifting through the void. The story of our sun begins not with fire, but with ice in the frozen womb of a molecular cloud, surrounded by thousands of sibling stars that have since scattered into the galaxy and been lost forever. Chapter 2: The Lost Family and the Supernova Trigger. 4.5 billion years ago, there was no sun. There was no Earth, no Moon, no Mars, no Jupiter. The space where our solar system now exists was occupied by nothing but darkness and cold. Floating in the void was a vast molecular cloud, a sprawling, shapeless mass of gas and dust that stretched across dozens of light years. These clouds are the nurseries of the galaxy, the places where stars are born, but they are also the graveyards, filled with the ashes of stars that died long ago. Our cloud was composed mostly of hydrogen and helium, the primordial elements forged in the Big Bang. But it was also laced with heavier elements: carbon, oxygen, nitrogen, silicon, iron, elements that could only have been created in the nuclear furnaces of massive stars and scattered into space when those stars exploded. This cloud was cold, unimaginably cold. The temperature hovered just 10 to 20 degrees above absolute zero, the coldest temperature physically possible. In this deep freeze, atoms barely moved. Thermal motion was almost non-existent. This is the first critical condition for star formation. The gas must be cold. Heat causes gas to expand and resist collapse. Cold allows gravity to take hold. For millions of years, perhaps tens of millions, this cloud drifted through the Orion spur of the Milky Way, a quiet ghost in the darkness. It was stable. The weak pressure of the gas and the faint support of magnetic fields were just enough to resist the pull of its own gravity. It might have remained that way forever, a dark, invisible presence in the galaxy, if not for a catastrophic event that happened nearby. We know today that the sun did not form in isolation. The evidence is written in stone, quite literally. Scientists have analyzed the oldest meteorites, rocky remnants from the very first days of the solar system, and found something astonishing. Embedded inside these ancient stones are the decay products of a radioactive isotope called aluminum-26. This is not the normal, stable version of aluminum that you find in soda cans. This is a short-lived, radioactive variant with a half-life of only 700,000 years. In cosmic terms, that is the blink of an eye. After a few million years, aluminum-26 decays completely into magnesium, leaving behind only a faint chemical fingerprint. The presence of aluminum-26 in the earliest solar system materials is a smoking gun. This isotope is not produced in normal stars like the sun. It is forged only in the extreme conditions found in massive stars or in the shockwaves of supernova explosions. The fact that we find evidence of it in the very first solids that condensed from the solar nebula means that aluminum-26 was injected into our cloud at the moment of our birth. It had to be fresh. If it had been floating around the galaxy for millions of years, it would have already decayed away. Someone, or rather, something, delivered a dose of freshly cooked radioactive material right as our solar system was forming. This discovery has led to one of the most compelling theories about the sun's origin, the Wolf-Rayet bubble hypothesis. The theory goes like this: our molecular cloud was not drifting alone in empty space. It was sitting on the edge of a massive bubble blown by a Wolf-Rayet star, a monstrous, unstable giant with a mass 40 to 50 times greater than the sun. These stars are the rock stars of the cosmos. They live fast, burn bright, and die young. As they near the end of their brief lives, They shed their outer layers in ferocious stellar winds, blowing a cavity in the surrounding interstellar medium. The wind sweeps up the gas like a snowplow, creating a dense shell of material at the boundary of the bubble. A molecular cloud was likely caught in this shell, slowly accumulating the debris shed by the dying giant. The Wolf-Rayet star enriched the cloud with fresh aluminum-26, along with other short-lived isotopes. Then came the inevitable end. The giant star ran out of fuel, its core collapsed, and it exploded in a supernova, one of the most violent events in the universe. The shockwave from that explosion slammed into our cloud like a tsunami hitting a wall of fog. It didn't just pass through, it compressed the gas, squeezing it, forcing atoms closer together. In some regions, the compression was enough to push the density past a critical threshold known as the Jeans mass. The Jeans mass is the tipping point where the internal pressure of a gas cloud can no longer support the weight of its own gravity. Once you cross that line, there is no turning back. Gravity wins. The collapse begins. What happened next was a gravitational freefall. A pocket of gas, one of many scattered throughout the cloud, began to shrink. As it shrank, it spun. This is the law of conservation of angular momentum, the same principle that makes an ice skater spin faster when she pulls her arms in. The cloud, which had been light years across and spinning slowly, collapsed into a disk spinning furiously. In the center of this disk, the material piled up. The pressure skyrocketed. The temperature began to rise. The cold, dark cloud was transforming into something new, a protostar. This was the birth of our sun, but it was nothing like the star we see today. The young sun was a T-Tauri star, a violent, unstable infant that had not yet ignited fusion. It was powered only by the heat of its own gravitational collapse. As gas fell inward, the potential energy was converted into thermal energy, causing the protostar to glow with a dull red light. But this was not a calm, serene object. T-Tauri stars are chaotic. They blast the surrounding space with intense X-rays and ultraviolet radiation. They generate powerful stellar winds that blow at hundreds of kilometers per second. The young sun roared to life, clearing the inner regions of the protoplanetary disk and halting the inward migration of material that would have otherwise spiraled into the star. This T-Tauri wind was crucial for the formation of the terrestrial planets. Without it, the inner solar system might have remained choked with gas, and Earth might have accreted a massive hydrogen envelope, becoming a gas giant instead of a rocky world. The wind swept away the remaining gas, leaving behind only the dust and solid particles that would eventually coalesce into Mercury, Venus, Earth, and Mars. In the process, the young sun also stripped away much of the primordial atmosphere from the inner protoplanets, leaving Mercury as little more than an exposed iron core. But here is the haunting part of the story. The sun was not born alone. The molecular cloud that collapsed to form our star was massive enough to spawn hundreds, perhaps thousands, of other stars. We were part of an open cluster, a dense stellar family, all born from the same nebula within a few million years of each other. If you could have stood on the surface of a newly formed asteroid 4.5 billion years ago and looked up at the night sky, you would not have seen the dark, lonely expanse we see today. You would have seen a sky ablaze with light. Hundreds of stars, some of them brighter than the full moon, would have crowded the heavens. These were our siblings, stars that shared the same chemical DNA, the same birthplace, the same history. For the first few 100 million years, this stellar family stayed together, bound by mutual gravity, moving through the galaxy as a cohesive unit. But gravity is a fickle companion. The Milky Way is not a calm, static environment. It is a turbulent, dynamic spiral of matter, full of tidal forces and gravitational disturbances. As our cluster orbited the galactic center, it was subjected to shearing forces from the galaxy's differential rotation. It passed near giant molecular clouds, whose gravity tugged at individual stars, pulling them away from the group. Slowly, one by one, the siblings drifted apart. The cluster dissolved. The sun was left alone, drifting through the Orion spur with only its planets for company. The brilliant, star-filled sky of our youth faded into the dark, empty expanse that we now call normal. For decades, astronomers believed these lost siblings were gone forever, scattered beyond recognition across the breadth of the galaxy. But in the age of big data and precision spectroscopy, we are finally finding them. The search for the Sun's siblings is a forensic investigation on a galactic scale. To identify a sibling, you must find a star with the exact same chemical composition as the Sun, the same ratios of iron, yttrium, barium, and dozens of other trace elements. You also have to analyze the star's motion through the galaxy and rewind the clock to see if it could have been in the same place as the Sun 4.5 billion years ago. In 2014, astronomers struck gold. They identified a star called HD 162826, located about 110 light-years away in the constellation Hercules. It is slightly more massive and hotter than the Sun, but its chemical fingerprint is a perfect match. It is our brother, a blood relative that drifted away billions of years ago. A few years later, another sibling was found, HD 186302, a star that is even more similar to the Sun, almost a twin. These stars are out there right now, shining in the night sky, likely hosting their own planets. There may be civilizations orbiting our lost siblings, looking back toward our Sun, seeing just another anonymous point of light, completely unaware that we are family. The discovery of these siblings confirms the violent, crowded nature of the Sun's birth. We are not the product of a quiet, isolated collapse. We are refugees from a dispersed cluster, survivors of a chaotic birth environment shaped by the death of a nearby giant star. And that environment left its mark on us. The aluminum-26 injected into the solar nebula didn't just sit there as a passive contaminant. It decayed, releasing heat. This radioactive decay was crucial for the early solar system. It melted the interiors of the first asteroids, allowing them to differentiate into iron cores and rocky mantles, a process that would later influence the formation of Earth's own iron core and magnetic field. As the cluster dispersed and the Sun entered its solitary adulthood, the chaos didn't end. The protostar at the center of the disk was still contracting, still growing hotter. For the first few million years, the Sun glowed only from the heat of gravitational collapse. It was a bloated, red ball of gas, far larger than the modern Sun, pulsating with instability. Then, finally, the core temperature crossed the threshold, 10 million degrees Celsius. At that temperature, hydrogen nuclei move fast enough to overcome their mutual electromagnetic repulsion and fuse together. Nuclear fusion ignited. The Sun became a true star. But here is where one of the greatest mysteries in solar system science emerges. When fusion first ignited, the Sun was not the bright, life-giving star we see today. Models of stellar evolution tell us that the infant Sun was about 30% dimmer than the modern Sun. This is because stars get brighter as they age. As hydrogen is converted into helium, the core becomes denser. To maintain the pressure needed to resist gravitational collapse, the core must get hotter. Hotter cores fuse hydrogen faster, producing more energy, which makes the star brighter. A 30% reduction in solar luminosity is catastrophic for a planet like Earth. Without the current level of solar energy, the surface temperature of the early Earth should have been well below freezing. The oceans should have been locked in ice. The planet should have been a snowball. And yet, the geological record tells a completely different story. We find sedimentary rocks that form in liquid water, dating back 3.8 billion years. We find evidence of early life swimming in liquid oceans at a time when the Sun should have been too weak to melt ice. This is the faint young sun paradox. How did Earth maintain liquid water under a dim star? The answer could lie in the atmosphere. Perhaps the early Earth had a much thicker blanket of greenhouse gases, carbon dioxide, methane, or even hydrogen, that trapped every scrap of heat and kept the surface warm. Or perhaps the young Sun was more massive than it is today, burning brighter in its youth before losing mass through intense stellar winds during the T-Tauri phase. Another possibility is that Earth's orbit was slightly different, or that the planet had more internal heat from radioactive decay and leftover gravitational energy from its formation. The answer to this paradox determines the habitability of the universe. If Earth survived the faint young Sun only because of a lucky combination of atmospheric gases, then planets like ours might be incredibly rare. If, on the other hand, the solution lies in stellar physics, if young stars naturally provide more warmth than our models predict, then habitable planets might be common. We still don't know the answer. The paradox remains one of the great unsolved mysteries of planetary science. As the Sun transitioned from a chaotic T-Tauri star to a stable, hydrogen-burning main-sequence star, it set the stage for the emergence of life. The violent birth was over. The cluster had dispersed. The disk of gas and dust was coalescing into planets. And deep in the core of the newborn star, a process began that would continue, uninterrupted, for billions of years. The fusion of hydrogen into helium, the engine that powers all life on Earth. But that engine is hidden from view. We cannot see it. We cannot touch it. To understand how the Sun truly works, we must leave the surface and descend into the depths. We must journey into the most extreme environment in the solar system, the core, where temperatures reach 15 million degrees, where pressures crush matter into a state unlike anything found on Earth, and where the impossible becomes inevitable. The next chapter of our story takes us into the engine room of the Sun, where hydrogen atoms are forced to do the unthinkable, and where the secret of the Sun's power finally reveals itself. Chapter 3: The Engine Room, the Proton-Proton Chain. To understand how the Sun stays alive, we must descend into the most extreme environment in the solar system. This is not a journey you can make with a spacecraft or a probe. No material known to science could survive the crushing pressures, the searing temperatures, and the torrential radiation that exist in the core of the Sun. This is a place where the normal rules of physics break down, where matter exists in a state so extreme that atoms are stripped naked, and where the impossible becomes routine. This is the engine room, the beating heart of the star. This is where the Sun generates its power. The core of the Sun is a sphere roughly 25% of the Sun's radius, extending about 175,000 kilometers from the center. It contains only about 2% of the Sun's total volume, but it holds 34% of its mass. This is where the density peaks at an astonishing 150 grams per cubic centimeter, more than 10 times the density of lead and 150 times the density of water. The temperature is 15 million degrees Celsius. At this temperature, atoms do not exist as we know them. Electrons are ripped away from their nuclei by the sheer violence of thermal motion. What remains is a plasma, a seething ocean of free protons, electrons, and helium nuclei, all moving at velocities measured in hundreds of kilometers per second. In this chaotic environment, hydrogen is being transformed into helium through a process called nuclear fusion. The specific mechanism the Sun uses is known as the proton-proton chain, and it is one of the most elegant and improbable processes in all of physics. To appreciate the miracle of the proton-proton chain, you must first understand the problem it solves. Protons are positively charged particles. The electromagnetic force causes like charges to repel. When two protons approach each other, they experience an enormous repulsive force that gets stronger the closer they come. This is called the Coulomb barrier, and it is a wall of electrical repulsion that keeps protons apart. Overcome this barrier and get close enough for the strong nuclear force to take over and bind them together, the protons would need to move at incredibly high speeds. Calculations show that to reliably smash through the Coulomb barrier, protons would need temperatures of billions of degrees. But the core of the Sun is only 15 million degrees. At that temperature, protons are moving fast, but not nearly fast enough to overcome the barrier through classical physics alone. By all rights, fusion should not be happening. The Sun should be a cold, dark ball of hydrogen, and yet it shines. The solution to this paradox is quantum mechanics. At the atomic scale, particles do not behave like tiny billiard balls. They behave like waves. When two protons collide in the core of the Sun, they do not need to actually overcome the Coulomb barrier. Instead, they have a tiny probability of quantum tunneling through it. Quantum tunneling is one of the strangest predictions of quantum physics. It states that there is a non-zero chance that a particle can simply appear on the other side of a barrier, even if it does not have enough energy to climb over it. The probability is extremely small, but it is not zero. In the core of the Sun, protons are colliding with each other trillions upon trillions of times every second. Most of these collisions result in nothing. The protons bounce off each other and go their separate ways. But every once in a while, in a 1 in a billion chance event, two protons tunnel through the barrier and get close enough for the strong nuclear force to grab them. When this happens, the protons fuse. But here is the critical detail: two protons cannot form a stable nucleus. If they simply stuck together, they would immediately fly apart. To create a stable product, one of the protons must undergo a transformation. It must convert into a neutron. This transformation is mediated by the weak nuclear force, the same force responsible for radioactive decay. In a process called beta-plus decay, one of the protons ejects a positron, which is the antimatter counterpart of an electron and an electron neutrino. The proton becomes a neutron. The result is a nucleus with one proton and one neutron, known as deuterium, a heavy isotope of hydrogen. This first step of the proton-proton chain is the bottleneck. It is extraordinarily slow. On average, a proton in the Sun's core will wander around for billions of years before it successfully fuses with another proton to create deuterium. This is why the Sun burns so slowly. If fusion were faster, the Sun would have exhausted its fuel billions of years ago. Once deuterium is formed, the process accelerates dramatically. Deuterium is far more reactive than lone protons. Within about 1 second, the newly formed deuterium nucleus collides with another proton and fuses to create helium-3, a light isotope of helium with 2 protons and 1 neutron. This reaction is mediated by the strong nuclear force, which is much faster than the weak force, and it releases a high-energy gamma-ray photon. The helium-3 nucleus then waits for another helium-3 nucleus to come along. When 2 helium-3 nuclei collide, they fuse to form helium-4, the stable, common isotope of helium with 2 protons and 2 neutrons. In the process, they spit out 2 protons, which are recycled back into the plasma to begin the chain again. This is the proton-proton chain in its simplest form. The net result is that 4 protons are converted into 1 helium-4 nucleus, 2 positrons, 2 neutrinos, and 2 gamma-ray photons. The mass of the helium-4 nucleus is slightly less than the combined mass of the 4 protons. That missing mass, about 0.7% of the original mass, is converted into energy. This is the source of the Sun's power. Every second, 600 million tons of hydrogen are fused into 596 million tons of helium, and the missing 4 million tons become the light and heat that sustain life on Earth. But the Sun also uses a second fusion pathway, though to a much lesser extent. This is the carbon-nitrogen-oxygen cycle, or CNO cycle. In this process, carbon, nitrogen, and oxygen nuclei act as catalysts, facilitating the fusion of hydrogen into helium. The CNO cycle is far more temperature-sensitive than the proton-proton chain. It becomes dominant in stars hotter and more massive than the Sun, where core temperatures exceed 17 million degrees Celsius. In the Sun, the CNO cycle contributes only about 1 to 2% of the total energy output, but even that small contribution is important. The CNO cycle produces neutrinos with different energies than the proton-proton chain, and detecting these neutrinos has allowed scientists to probe the interior of the Sun in ways that would otherwise be impossible. Neutrinos are the ghosts of the subatomic world. They are nearly massless particles that barely interact with matter. A neutrino can pass through a light-year of solid lead and have only a 50-50 chance of interacting with a single atom. Trillions of neutrinos produced in the Sun's core pass through your body every second, day and night, without you ever noticing. They stream out of the Sun at the speed of light, carrying information about the fusion reactions happening deep in the core. Unlike photons, which take tens of thousands of years to escape the Sun, neutrinos escape in about 2 seconds. They are the only direct messengers from the core. For decades, scientists tried to detect these solar neutrinos to confirm that fusion was really happening in the Sun. In the 1960s, a pioneering experiment led by physicist Raymond Davis was set up deep in the Homestake gold mine in South Dakota. The detector consisted of a giant tank filled with 615 tons of cleaning fluid, specifically chosen because it contained chlorine-37, which can capture neutrinos and transform into argon-37. The experiment ran for nearly 30 years and it detected neutrinos, but there was a problem. It only detected about 1/3 of the expected number. This discrepancy became known as the solar neutrino problem, and it haunted astrophysicists for decades. The solution came in 2001 from the Sudbury Neutrino Observatory, or SNO, in Canada. SNO used a detector filled with heavy water made with deuterium instead of normal hydrogen. This allowed the experiment to detect not only electron neutrinos, which are produced in the Sun, but also the other two types of neutrinos, muon neutrinos and tau neutrinos. The results were stunning. The total number of neutrinos detected matched the predictions perfectly, but only about 1/3 of them were electron neutrinos. The other 2/3 had transformed into the other types during their journey from the core to Earth. This was the first direct proof of neutrino oscillation, a quantum phenomenon where neutrinos change flavor as they travel. The Sun was producing the right number of neutrinos all along. We were just not detecting all of them. The neutrino experiments confirmed what we had long suspected. The Sun is powered by the fusion of hydrogen into helium, and the proton-proton chain is the dominant mechanism. But knowing the source of the energy is only the beginning. The energy created in the core must somehow travel outward to the surface and escape into space. This journey is long, tortuous, and governed by processes that turn the Sun into a cosmic onion with distinct layers, each with its own physics. The next layer, the one immediately surrounding the core, is the radiative zone, and it is a prison for light. Chapter 4, The 100,000-Year Walk, the Radiative Zone. The energy born in the core of the Sun does not escape easily. Surrounding the core is a vast, oppressive region known as the radiative zone, a layer that extends from the edge of the core at about 0.25 solar radii all the way out to about 0.7 solar radii. This is a region of the Sun where energy transport happens not by convection, not by conduction, but by radiation. Photons created in the core must fight their way through this zone, and the journey is agonizingly slow. This is the 100,000-year walk, the longest and most frustrating commute in the solar system. To understand why the radiative zone is so difficult to traverse, you must first understand the concept of opacity. Opacity is a measure of how much matter blocks or scatters light. In the radiative zone, the plasma is incredibly dense and incredibly hot. Temperatures range from 7 million degrees Celsius near the outer edge to 15 million degrees near the core. The density is high enough that the average distance a photon can travel before it is absorbed or scattered is measured in millimeters. This distance is called the mean free path, and in the radiative zone, it is vanishingly small. When a gamma-ray photon is emitted from a fusion reaction in the core, it immediately slams into a nearby particle, usually an electron or a proton. The photon is absorbed, and the particle gains energy. A fraction of a second later, the particle re-emits the photon, but in a completely random direction. The photon then travels another millimeter or so before it is absorbed again. This process repeats trillions upon trillions of times. The photon is not moving in a straight line toward the surface. It is undergoing a random walk. A chaotic, three-dimensional drunkards stumble through a crowd so dense that progress is almost imperceptible. The mathematics of random walks tells us that the time it takes for a photon to diffuse through the radiative zone depends on the square of the distance it must travel. The radiative zone is roughly 300,000 kilometers thick. If a photon could travel in a straight line at the speed of light, it would cross this distance in 1 second, but it cannot. It is forced to take a path that is trillions of times longer, zigzagging randomly, often moving backward toward the core before eventually, by sheer statistical luck, drifting outward. The result is that the average photon takes between 100,000 and 170,000 years to cross the radiative zone and reach the convective zone above. During this journey, something remarkable happens to the photon. When it was born in the core, it was a high-energy gamma ray, a killer capable of ripping apart molecules and ionizing atoms. But every time the photon is absorbed and re-emitted, it loses a little bit of energy. The particles in the plasma are cooler than the photon, so when they absorb and re-emit it, they steal some of its energy and convert it into thermal motion. Over thousands of absorptions, the gamma ray is gradually downshifted in frequency. It becomes an X-ray, then an ultraviolet photon, then visible light, then infrared. By the time the photon reaches the top of the radiative zone, it has been completely transformed. This energy degradation is not a loss. It is a conversion. The energy that was once concentrated in a single, high-energy photon is now spread out among many low-energy photons. This is how the sun's energy is thermalized. The violent, concentrated output of the core is smoothed out into a steady flow of heat. The radiative zone acts as a giant buffer, storing energy and releasing it slowly. This is why the sun's brightness is so stable. Even if the fusion rate in the core were to fluctuate, the radiative zone would absorb those fluctuations, and the surface would continue to shine with the same steady glow for thousands of years. The physics of radiation transport in the radiative zone is governed by a process called radiative diffusion. This is not the same as radiation simply flying through empty space. It is diffusion, the same process that causes a drop of food coloring to slowly spread through a glass of water. The photons are jostled and scattered, spreading outward from the hot core to the cooler outer layers, driven by the temperature gradient. The steeper the temperature gradient, the faster the diffusion. But even at its fastest, the process is glacially slow by human standards. The opacity of the radiative zone depends on the composition and temperature of the plasma. In the sun, the dominant source of opacity is electron scattering, a process where photons bounce off free electrons. The cross-section for this process, known as Thomson scattering, is small but not negligible. In a plasma as dense as the radiative zone, even a small scattering cross-section is enough to make the material nearly opaque. Other sources of opacity include free absorption, where a photon is absorbed by a free electron in the presence of an ion, and bound free absorption, where a photon ionizes a bound electron. Together, these processes make the radiative zone one of the most opaque regions in the universe. There is no motion in the radiative zone, at least not large-scale motion. The plasma is stable, stratified by density and temperature. There are no convection currents, no churning, no mixing. The energy moves, but the matter stays put. This is in stark contrast to the layer above, where everything is in constant motion. The radiative zone is a quiet, still prison where energy slowly diffuses outward while the matter remains frozen in place. But the radiative zone is not entirely without structure. As photons diffuse outward, they carry not only energy but also momentum. The outward flow of radiation exerts a pressure on the plasma, a force known as radiation pressure. In the sun, radiation pressure is a significant contributor to the total pressure that holds the star up against gravity. In more massive stars, radiation pressure can become the dominant force, sometimes so strong that it blows the outer layers of the star away in powerful stellar winds. In the sun, radiation pressure is important but not dominant. It is gravity and thermal pressure that do most of the work. As we move outward through the radiative zone, the temperature drops and the density decreases. At the outer edge of the radiative zone, the temperature has fallen to about 2 million degrees Celsius. At this point, the conditions change. The plasma becomes less ionized. Heavier elements like carbon, nitrogen, and oxygen begin to hold onto some of their electrons. These partially ionized atoms are much more efficient at absorbing photons than fully ionized hydrogen and helium. The opacity spikes. The radiative zone can no longer transport energy efficiently. The temperature gradient becomes too steep. The plasma becomes unstable. This is the boundary between the radiative zone and the convective zone, and it is one of the most important transitions in the entire star. Below this boundary, energy moves by radiation. Above it, energy moves by convection. The plasma begins to boil. What was once a still, quiet layer becomes a churning, turbulent cauldron. We have reached the outer third of the sun's interior, where the real chaos begins. This is the convective zone, and it is a place of perpetual motion, where hot plasma rises and cool plasma sinks in an endless cycle that has been running for billions of years. This is where the sun's surface phenomena are born, where magnetic fields are twisted and amplified, and where the energy that began its journey in the core finally approaches freedom. But before we can understand the surface, we must first understand the mechanism that drives the convection. We must watch the plasma rise and fall, and witness the birth of the structures that give the sun its texture and its fury. Each chapter must be at least 2,000 words long. Remake, chapters 3 and 4. Chapter 3: The Engine Room, the Proton-Proton Chain. To understand how the Sun stays alive, we must descend into the most extreme environment in the solar system. This is not a journey you can make with a spacecraft, a probe, or any instrument built by human hands. No material known to science could survive even a fraction of a second in the conditions that exist at the core of the Sun. The temperatures would vaporize steel, diamond, and tungsten in an instant. The pressures would crush matter into states that do not exist anywhere on Earth. The radiation would annihilate biological tissue faster than nerves could register pain. This is a place where the normal rules of physics break down, where atoms are stripped naked, their electrons ripped away by the sheer violence of thermal motion, and where the impossible becomes not only possible, but routine. This is the engine room, the beating heart of the star, the place where the Sun generates its power. This is where we must go to understand the source of all light, all warmth, and all life in the solar system. The core of the Sun is a sphere roughly 25% of the Sun's radius, extending about 175,000 kilometers from the absolute center of the star. This region contains only about 2% of the Sun's total volume, but it holds an astonishing 34% of its mass. The density at the center is approximately 150 grams per cubic centimeter, which is more than 10 times the density of lead, 20 times the density of iron, and 150 times the density of water. If you could somehow take a teaspoon of material from the Sun's core and bring it to Earth, it would weigh more than a solid block of steel the same size. But this is not solid material. It is plasma, a seething ocean of free protons, electrons, and helium nuclei, all moving at velocities measured in hundreds of kilometers per second. The temperature at the core is 15 million degrees Celsius. To put that in perspective, the surface of the Sun is only about 5,500 degrees Celsius. The core is nearly 3,000 times hotter. At this temperature, atoms do not exist as we know them. The kinetic energy of the particles is so high that electrons cannot remain bound to their nuclei. They are torn away, leaving behind naked atomic nuclei surrounded by a sea of free electrons. This state of matter, where electrons and nuclei move independently, is called a plasma. The Sun is not a ball of gas, it is a ball of plasma, and the core is the most extreme plasma environment in the solar system. In this chaotic, superheated environment, hydrogen is being transformed into helium through a process called nuclear fusion. The specific mechanism the Sun uses is known as the proton-proton chain, and it is one of the most elegant, improbable, and essential processes in all of physics. To appreciate the sheer unlikelihood and brilliance of this process, you must first understand the fundamental problem it solves. Protons are positively charged particles. The electromagnetic force, one of the four fundamental forces of nature, causes particles with the same charge to repel each other. When two protons approach one another, they experience an enormous repulsive force that grows exponentially stronger the closer they get. This repulsive force is called the Coulomb barrier, and it is a wall of electrical repulsion that keeps protons apart. To overcome this barrier and bring two protons close enough for the strong nuclear force to grab them and bind them together, the protons would need to move at incredibly high speeds. Classical physics calculations show that to reliably smash through the Coulomb barrier, protons would need temperatures of several billion degrees Celsius. But the core of the Sun is only 15 million degrees. At that temperature, protons are moving fast, but not nearly fast enough to overcome the barrier through brute force alone. By all rights, classical physics says fusion should not be happening in the Sun. The protons should bounce off each other and go their separate ways. The Sun should be a cold, dark, lifeless ball of hydrogen drifting through space, and yet the Sun shines. For 4.6 billion years, it has been shining. So what is happening? The solution to this paradox lies in one of the strangest and most counterintuitive predictions of quantum mechanics: quantum tunneling. At the atomic and subatomic scale, particles do not behave like tiny billiard balls. They behave like waves. In quantum mechanics, a particle's position is not a fixed point. It is described by a probability wave. When two protons collide in the core of the Sun, they do not need to have enough energy to actually climb over the Coulomb barrier. Instead, there is a small but non-zero probability that the wave function of one proton will tunnel through the barrier and appear on the other side, where the strong nuclear force is waiting to grab it. This probability is described by something called the Gamow factor, named after physicist George Gamow, who first calculated it in 1928. The Gamow factor tells us the probability that two protons with a given kinetic energy will successfully tunnel through the Coulomb barrier and fuse. For the temperatures and energies found in the Sun's core, this probability is extraordinarily small. The chance of any two specific protons successfully fusing is roughly 1 in a billion. But here is the key. The Sun's core is so massive and the number of protons so vast that even with these absurdly low probabilities, trillions upon trillions of fusion reactions are happening every second. The sheer statistical weight of numbers turns the impossible into the inevitable. When two protons do successfully tunnel through the barrier and come into contact, something remarkable happens, but they do not simply stick together. Two protons by themselves cannot form a stable nucleus. If they just fused into a diproton, a nucleus with two protons and no neutrons, it would immediately fly apart. The electromagnetic repulsion would tear it back into two separate protons in a fraction of a second. To create a stable product, one of the protons must undergo a transformation. It must convert into a neutron. This transformation is mediated by the weak nuclear force, the same force responsible for radioactive beta decay. In a process called beta plus decay, one of the protons emits a positron, which is the antimatter counterpart of an electron and an electron neutrino. The proton becomes a neutron. The result is a nucleus with one proton and one neutron, known as deuterium, a heavy isotope of hydrogen. This first step of the proton-proton chain is the bottleneck of the entire process. The weak force is, as its name suggests, weak. It operates on timescales that are extraordinarily long by nuclear standards. On average, a proton in the Sun's core will wander around for 9 billion years before it successfully fuses with another proton to create deuterium. This is why the Sun burns so slowly and steadily. If fusion were faster, the Sun would have exhausted its hydrogen fuel billions of years ago, and we would not be here. But once deuterium is formed, the process accelerates dramatically. Deuterium is far more reactive than lone protons. Within about 1 second of being created, the deuterium nucleus collides with another proton and fuses to create helium-3, a light isotope of helium with two protons and one neutron. This reaction is mediated by the strong nuclear force, which is millions of times faster than the weak force. The fusion of deuterium and a proton releases a high-energy gamma-ray photon, a packet of electromagnetic radiation so energetic that it would kill you instantly if you were exposed to it. This photon is born in the core and begins a journey that will take tens of thousands of years to complete, a journey we will explore in the next chapter. The helium-3 nucleus does not remain alone for long. It waits, drifting through the plasma until it encounters another helium-3 nucleus. When two helium-3 nuclei collide, they fuse to form helium-4, the stable, common isotope of helium with two protons and two neutrons. In the process, they spit out two protons, which are recycled back into the plasma to begin the proton-proton chain all over again. This is the beauty of the cycle. It is self-sustaining. The protons that are released can go on to create more deuterium, which creates more helium-3, which creates more helium-4, and the cycle continues. The net result of the proton-proton chain is that 4 protons are converted into one helium-4 nucleus, 2 positrons, 2 neutrinos, and several gamma-ray photons. The mass of the helium-4 nucleus is slightly less than the combined mass of the 4 protons that went into making it. The difference is about 0.7% of the original mass. That missing mass has not disappeared. It has been converted into energy in accordance with Einstein's equation. Energy equals mass times the speed of light squared. This is the source of the Sun's power. Every second, 600 million tons of hydrogen are fused into 596 million tons of helium, and the missing 4 million tons become the light and heat that sustain life on Earth. But the proton-proton chain is not the only fusion pathway operating in the Sun. There is a second mechanism called the carbon-nitrogen-oxygen cycle, or CNO cycle. In this process, carbon, nitrogen, and oxygen nuclei act as catalysts, facilitating the fusion of hydrogen into helium without being consumed themselves. The CNO cycle is far more sensitive to temperature than the proton-proton chain. It becomes the dominant energy source in stars hotter and more massive than the Sun, where core temperatures exceed 17 million degrees Celsius. In the Sun, the CNO cycle contributes only about 1 to 2% of the total energy output, but even that small contribution is important for astrophysics. The CNO cycle produces neutrinos with different energies than the proton-proton chain, and by detecting these neutrinos, scientists can probe the interior of the Sun and test their models of stellar structure. Neutrinos are the ghosts of the particle world. They are nearly massless particles that barely interact with matter. A neutrino can pass through a light-year of solid lead and have only a 50-50 chance of interacting with a single atom. Trillions of neutrinos produced in the Sun's core pass through your body every second, day and night, without you ever noticing. They stream out of the Sun at the speed of light, carrying with them direct information about the fusion reactions happening deep in the core. Unlike photons, which take tens of thousands of years to diffuse through the Sun's interior, neutrinos escape in about 2 seconds. They are the only direct messengers from the engine room. For decades, scientists tried to detect these solar neutrinos to confirm that fusion was really happening inside the Sun. In the 1960s, a pioneering experiment led by physicist Raymond Davis was set up deep in the Homestake gold mine in South Dakota. The detector consisted of a giant tank filled with 615 tons of cleaning fluid, specifically chosen because it contained chlorine-37, an isotope that can capture neutrinos and transform into argon-37, a radioactive isotope that can be detected. The experiment ran for nearly 30 years, and it detected neutrinos. But there was a problem. It only detected about 1/3 of the expected number. This discrepancy became known as the solar neutrino problem, and it haunted astrophysicists for decades. The solution came in 2001 from the Sudbury Neutrino Observatory, or SNO, located deep underground in a nickel mine in Ontario, Canada. SNO used a detector filled with heavy water made with deuterium instead of normal hydrogen. This allowed the experiment to detect not only electron neutrinos, which are the type produced in the Sun, but also the other 2 types or flavors of neutrinos, muon neutrinos and tau neutrinos. The results were stunning and revolutionary. The total number of neutrinos detected matched the predictions perfectly. The Sun was producing exactly the right number of neutrinos, but only about 1/3 of them arriving at Earth were still electron neutrinos. The other 2/3 had transformed or oscillated into the other 2 flavors during their journey from the Sun's core to Earth. This was the first direct proof of neutrino oscillation, a quantum mechanical phenomenon where neutrinos change flavor as they travel through space. The discovery confirmed that neutrinos have mass, however small, and it vindicated decades of solar models. The Sun was producing the right number of neutrinos all along. We were just not detecting all of them because we were only looking for one flavor. The neutrino experiments confirmed what scientists had long suspected. The Sun is powered by the fusion of hydrogen into helium, and the proton-proton chain is the dominant mechanism. But knowing the source of the energy is only the beginning of the story. The energy created in the core, in the form of high-energy gamma-ray photons, does not simply beam out of the Sun and into space. It must somehow travel outward from the core to the surface, a distance of nearly 700,000 kilometers. This journey is long, tortuous, and governed by physics that turn the Sun into a cosmic onion with distinct layers, each with its own unique behavior and characteristics. The layer immediately surrounding the core is called the radiative zone, and it is a prison for light, a place where photons are trapped for tens of thousands of years, slowly fighting their way toward freedom. This is where we go next, into the darkness, into the random walk, into the longest commute in the solar system. Chapter 4, the 100,000-year walk, the radiative zone. The energy born in the core of the Sun does not escape easily. Surrounding the fusion furnace is a vast, oppressive region known as the radiative zone, a layer that extends from the edge of the core at roughly 0.25 solar radii all the way out to about 0.7 solar radii, encompassing nearly 45% of the Sun's radius. This is a region of the Sun where energy transport happens not by the physical motion of material, not by convection, and not by conduction, but purely by radiation. Photons created in the core, or created through interactions in the radiative zone itself, must fight their way through this dense, opaque plasma, and the journey is agonizingly, incomprehensibly slow. This is the 100,000-year walk, the longest and most frustrating commute in the solar system, a journey that transforms the violent gamma rays of the core into the gentle, life-giving light that reaches Earth. To understand why the radiative zone is so difficult to traverse, you must first understand the concept of opacity, a fundamental property of matter that describes how effectively it blocks or scatters light. Opacity is not just about whether something is see-through or not. It is a quantitative measure of how far light can travel through a material before it is absorbed or scattered. In the radiative zone, the plasma is incredibly dense and incredibly hot. Temperatures range from approximately 7 million degrees Celsius near the outer boundary to 15 million degrees near the core. The density is also high, though it decreases as you move outward. Near the core, the density is comparable to solid lead. Farther out, it drops to the density of water, and then lower still, but even at its least dense, the radiative zone is far denser than the air you are breathing right now. In this environment, the average distance a photon can travel before it is absorbed or scattered is measured in millimeters or even fractions of a millimeter. This tiny distance is called the mean free path. To put that in perspective, the radiative zone is roughly 300,000 kilometers thick. If a photon could travel in a straight line at the speed of light, it would cross this distance in 1 second, but it cannot. It is forced to take a path that zigzags, meandering, bouncing and stumbling through the plasma like a drunkard trying to find the exit in a pitch-black, infinitely crowded room. When a gamma-ray photon is emitted from a fusion reaction in the core, or when a photon is re-emitted by an atom in the lower layers of the radiative zone, it immediately slams into a nearby particle, usually a free electron or proton. The photon is absorbed, and the particle gains a tiny amount of energy. A fraction of a second later, the particle re-emits a photon, but in a completely random direction. There is no memory of the original direction. The photon could be re-emitted back toward the core, sideways, or outward. The direction is determined purely by chance. This process is called scattering. The dominant scattering process in the radiative zone is Thomson scattering, the elastic scattering of photons by free electrons. Thomson scattering is a classical electromagnetic effect where photons' oscillating electric field causes a free electron to oscillate. The oscillating electron, in turn, emits a new photon at the same frequency as the original. The photon's energy does not change significantly in each individual scattering event, only its direction changes. The cross-section for Thomson scattering, the effective area over which an electron can capture and scatter a photon, is about 0.665 barns, or 6.65 times 10 to the negative 29 square meters. This is an incredibly small area, but in a plasma with a density of billions of trillions of particles per cubic centimeter, even a small cross-section is enough to make the material nearly opaque. This begins what scientists call the random walk. The photon travels a fraction of a millimeter, collides with an electron, and is scattered in a random direction. It travels another fraction of a millimeter, collides again and scatters again. It bounces left, then right, then down toward the core, then up again, then sideways. Over and over and over, trillions upon trillions of times. The photon is not making progress in a straight line. It is wandering aimlessly, trapped in a three-dimensional maze with no walls, only endless obstacles. The mathematics of random walks tells us that the time it takes for a photon to diffuse from the core to the edge of the radiative zone depends on the square of the distance divided by the mean free path. The larger the distance, the longer the journey, and the smaller the mean free path. The more times the photon must scatter. The result is that the average photon created in the core takes somewhere between 100,000 and 170,000 years to cross the radiative zone and reach the convective zone above. Think about that for a moment. The light that touched your face this morning, the light that warmed your skin and illuminated the world around you, began its journey not yesterday, not last year, not even in the last century. It began its journey when Homo sapiens were just beginning to migrate out of Africa, when early humans were learning to make stone tools and control fire. While humanity invented language, built civilizations, discovered agriculture, fought wars, invented the wheel, and walked on the moon, that photon was still trapped inside the sun, slowly, painstakingly fighting its way out. It only reached the surface about 8 minutes ago, finally free to race across the vacuum at the speed of light and strike your retina. During this journey, something remarkable happens to the photon. When it was born in the core, it was a high-energy gamma ray, a killer, a photon so energetic that it could rip electrons away from atoms and shatter molecular bonds. But every time the photon is absorbed and re-emitted, it loses a tiny bit of energy. The particles in the plasma are cooler than the photon, so when they absorb it, they steal some of its energy and convert it into thermal motion. Over thousands and thousands of absorptions and re-emissions, the gamma ray is gradually downshifted in frequency. It becomes an X-ray, then an ultraviolet photon, then visible light, then infrared, then radio waves. By the time the photon reaches the top of the radiative zone, it has been completely transformed. The violent, concentrated energy of the core has been thermalized, spread out among many lower energy photons. This energy degradation is not a loss, it is a conversion. The energy that was once concentrated in a single, high-energy photon is now distributed among many low-energy photons, and the total energy is conserved. This is how the sun's energy is thermalized. The violent, concentrated output of fusion reactions in the core is smoothed out into a steady, diffuse flow of heat. The radiative zone acts as a giant buffer, a cosmic capacitor that stores energy and releases it slowly and steadily. This is why the sun's brightness is so stable, why it does not flicker and pulse like some other stars. Even if the fusion rate in the core were to fluctuate, the radiative zone would absorb those fluctuations, smoothing them out over tens of thousands of years. The surface would continue to shine with the same steady glow, powered by the fossil energy slowly leaking out from the interior. The physics of radiation transport in the radiative zone is governed by a process called radiative diffusion. This is not the same as radiation simply flying through empty space. It is diffusion, the same process that causes a drop of ink to slowly spread through a glass of water or heat to slowly spread through a metal bar. The photons are jostled, scattered, and pushed outward from the hot core to the cooler outer layers, driven by the temperature gradient. The steeper the temperature gradient, the faster the diffusion. But even at its fastest, the process is glacially slow by any human standard. The opacity of the radiative zone, the factor that determines how difficult it is for photons to escape, depends on the composition, density, and temperature of the plasma. In stellar astrophysics, scientists use something called the Rosseland mean opacity, a weighted average of the opacity across all wavelengths, to describe how opaque a stellar interior is to radiation. The Rosseland mean opacity depends strongly on temperature. As the temperature increases, the plasma becomes more ionized. Electrons are stripped from their atoms, and the atoms can no longer absorb photons at specific wavelengths. This reduces the opacity. On the other hand, free absorption, where a photon is absorbed by a free electron in the presence of an ion, increases with temperature. The balance between these competing effects determines how opaque the radiative zone is. In the Sun, the dominant source of opacity in the radiative zone is electron scattering, primarily Thomson scattering. The cross-section for this process is small, but the sheer number of free electrons makes it the primary obstacle for photons trying to escape. Other sources of opacity include free absorption, where photons are absorbed and immediately re-emitted at a lower energy, and bound-free absorption, where photons ionize atoms by kicking electrons out of their orbits. Together, these processes make the radiative zone one of the most opaque environments in the universe. There is no motion in the radiative zone, at least not large-scale motion. The plasma is stable, stratified by density and temperature. There are no convection currents, no churning, no bulk flows of material. The energy moves outward, but the matter stays put. This is in stark contrast to the layer above, where everything is in constant, violent motion. The radiative zone is a quiet, still prison where energy slowly diffuses outward, while the matter remains essentially frozen in place, held in hydrostatic equilibrium by the balance between gravity and pressure. But the radiative zone is not entirely without influence. As photons diffuse outward, they carry not only energy but also momentum. The outward flow of radiation exerts a force on the plasma called radiation pressure. In the Sun, radiation pressure is a significant contributor to the total pressure that holds the star up against gravity. In the core, radiation pressure accounts for a small fraction of the total pressure. Thermal pressure, the pressure from the kinetic motion of particles, is dominant. But in more massive stars, radiation pressure can become the dominant force, sometimes so strong that it blows the outer layers of the star away in powerful stellar winds. In the Sun, radiation pressure is important but not dominant. It is gravity and thermal pressure that do most of the work of holding the star together. As we move outward through the radiative zone, the temperature drops and the density decreases. The pressure drops as well. At the outer edge of the radiative zone, about 70% of the way from the center to the surface, the temperature has fallen to approximately 2 million degrees Celsius. At this point, the conditions begin to change in a fundamental way. The plasma becomes less ionized. Heavier elements like carbon, nitrogen, and oxygen, which were completely stripped of their electrons deeper in the star, begin to recapture some of their outer electrons. These partially ionized atoms are much more efficient at absorbing photons than the fully ionized hydrogen and helium that dominate the deeper layers. The opacity spikes dramatically. When the opacity increases, the radiative zone can no longer transport energy efficiently. The temperature gradient, the rate at which temperature drops with distance, becomes steeper and steeper. At some point, the gradient becomes so steep that the plasma becomes unstable. This instability is described by something called the Schwarzschild criterion for convective stability. The Schwarzschild criterion states that a layer of gas in a star is stable against convection if the temperature gradient is not too steep. But if the temperature gradient exceeds a critical value, the layer becomes unstable. A blob of plasma that is displaced upward will be hotter than its surroundings, and because it is hotter, it is less dense. Being less dense, it is buoyant, and it continues to rise. A blob displaced downward is cooler and denser than its surroundings, and it continues to sink. This is convection, and it is the mechanism that transports energy in the outer third of the Sun. This is the boundary between the radiative zone and the convective zone, one of the most important transitions in the entire star. Below this boundary, energy moves by radiation, slowly diffusing outward over tens of thousands of years. Above it, energy moves by convection, carried by the bulk motion of plasma that rises, cools, sinks, and rises again in an endless cycle. The plasma begins to boil. What was once a still, quiet layer becomes a churning, turbulent ocean of superheated gas. We have reached the outer third of the Sun's interior, the convective zone, and it is a place of perpetual motion, a place where hot plasma rises to the surface at hundreds of meters per second, releases its energy, and sinks back down to be reheated. This is where the Sun's visible surface phenomena are born. This is where magnetic fields are twisted and amplified. This is where the energy that began its journey in the core, tens of thousands of years ago, finally approaches freedom and prepares to escape into space. But before we can understand the surface, we must first understand the mechanism that drives the convection and witness the birth of the structures that give the Sun its texture, its fury, and its voice. Chapter 5: The Tachocline, the Seat of the Mystery. Between the radiative zone and the convective zone lies one of the most enigmatic and critically important boundaries in the entire Sun. This is not a sharp, well-defined interface. It is a thin transition layer, a region only a few thousand kilometers thick, where the physics of the Sun undergoes a dramatic transformation. This layer is called the tachocline, and it is the seat of one of the greatest unsolved mysteries in solar physics, the origin of the Sun's magnetic field. The tachocline is a shear layer, a place where different parts of the Sun slide past each other at different speeds, twisting and stretching magnetic field lines until they snap. It is the dynamo engine that powers the Sun's magnetic activity, the birthplace of sunspots, solar flares, and coronal mass ejections. It is also a place we cannot see, cannot directly measure, and can only infer through indirect observations and complex computer. The tachocline sits at the base of the convective zone, roughly 70% of the way from the center of the Sun to the surface, at a radius of about 500,000 kilometers from the core. Above this boundary, the Sun rotates differentially. The equator spins faster than the poles, completing a full rotation in about 25 days, while the polar regions take closer to 35 days. This differential rotation is visible at the surface, where we can track the motion of sunspots and measure the rotation rate at different latitudes. Below the tachocline, in the radiative zone, the Sun rotates almost like a solid body. The rotation rate is nearly constant at all latitudes. The tachocline is the narrow transition region where the rotation profile changes from solid body rotation to differential rotation. This creates an enormous amount of shear, a velocity difference that stretches across thousands of kilometers. Shear is the enemy of stability. When different layers of fluid move at different speeds, they rub against each other, generating turbulence and twisting anything embedded in the flow. In the case of the Sun, what is embedded in the flow is the magnetic field. The Sun's magnetic field is not a permanent, static feature like the Earth's magnetic field, which is generated by a solid iron core. The Sun's field is dynamic, constantly being created, destroyed, and reshaped by the motion of the plasma. This process is called the solar dynamo. The dynamo works through a combination of two effects, known in the scientific community as the omega effect and the alpha effect. The omega effect is the easier of the two to understand. It is simply the stretching and winding of magnetic field lines by differential rotation. Imagine a magnetic field line that runs north-south, from the Sun's north pole to its south pole. As the Sun rotates, the equator spins faster than the poles. The part of the field line near the equator gets dragged along faster than the parts near the poles. Over time, the field line is stretched and wrapped around the Sun in the east-west direction, creating a toroidal magnetic field, a field that wraps around the Sun like the coils of a spring. This is the omega effect, and it is incredibly efficient in the tachocline, where the shear is strongest. The toroidal field generated by the omega effect can become extraordinarily strong. Calculations and simulations suggest that magnetic fields in the tachocline can reach strengths of 100,000 Gauss or 100 kilogauss. To put that in perspective, the Earth's magnetic field at the surface is about 0.5 Gauss. A hospital MRI machine generates about 10,000 to 30,000 Gauss. A 100,000 Gauss magnetic field is strong enough to rip atoms apart, aligning their electrons into quantum states that would be impossible under normal conditions. These fields are stored in the tachocline for months or years, building up strength until they become buoyant and rise through the convective zone to the surface, where they emerge as sunspots. But the omega effect alone is not enough to explain the solar dynamo. If all the dynamo did was stretch north-south field lines into east-west field lines, the system would run down. Eventually, all the north-south field would be converted into east-west field, and the dynamo would stop. To keep the dynamo running, there must be a mechanism to regenerate the north-south field from the east-west field. This is the alpha effect, and it is far more mysterious and poorly understood than the omega effect. The alpha effect is believed to be driven by the turbulent, helical motions of convective plasma rising through the convective zone. As the plasma twists and churns, it can twist the magnetic field lines, converting toroidal field back into poloidal field, the north-south component. This process is incredibly complex, involving small-scale turbulence, the Coriolis force from the Sun's rotation, and magnetic buoyancy instabilities. Despite decades of research, scientists still do not have a complete, satisfactory theory of how the alpha effect works. Some numerical simulations suggest that the alpha effect might be too weak to sustain the solar dynamo, leading to alternative theories that invoke magnetic buoyancy instabilities in the tachocline itself as a way to regenerate the poloidal field. One of the most puzzling aspects of the tachocline is why it is so thin. The transition from solid body rotation to differential rotation happens over a distance of only a few thousand kilometers, a tiny fraction of the sun's radius. If the radiative zone and the convective zone were simply rubbing against each other, you would expect the shear layer to spread out over time due to viscosity and turbulence. The tachocline should be getting thicker, but it is not. Observations from heliosismology, the study of sound waves traveling through the sun, show that the tachocline has remained thin and stable for at least the past few solar cycles. Something is confining it, keeping it sharp and narrow. Several theories have been proposed to explain the confinement of the tachocline. One possibility is that the magnetic field itself is responsible. Magnetic fields can exert forces on the plasma, and a strong toroidal field in the tachocline could resist the spreading of the shear layer, holding it in place. Another possibility is that there is a layer of fossil magnetic field left over from the sun's formation, buried deep in the radiative zone, that acts as a barrier to the spreading of the tachocline. A third possibility involves the interaction between rotation and gravity waves propagating through the sun's interior. The truth is, we do not know. The tachocline is one of the great unsolved problems in solar physics. What we do know is that the tachocline is critically important for the sun's magnetic activity. Without the tachocline, there would be no strong toroidal magnetic fields. Without strong toroidal fields, there would be no sunspots, no solar flares, no coronal mass ejections. The sun would be magnetically quiet, a stable, boring star with no space weather. The fact that the tachocline exists and that it is thin and stable is what makes the sun the active, dynamic star that it is. It is the engine that drives the 11-year solar cycle, the periodic rise and fall of magnetic activity that has been observed for centuries. The tachocline is also a window into the deep interior of the sun. Because it is the boundary between two very different regions, it influences the way sound waves propagate through the star. Heliosismology has allowed scientists to map the tachocline's location, thickness, and rotation profile with remarkable precision. By analyzing the frequencies of sound waves that ripple across the sun's surface, scientists can infer the internal structure of the star, much like geologists use seismic waves from earthquakes to probe the interior of the Earth. Heliosismology has revealed that the tachocline is not perfectly smooth. It has structure, with variations in thickness and rotation rate at different latitudes. These variations may be linked to the generation and transport of magnetic fields, but the details are still being worked out. The tachocline is a place of incredible shear, incredible magnetic field strength, and incredible scientific importance. It is the boundary where the quiet, stable radiative zone meets the violent, churning convective zone. It is the birthplace of the sun's magnetic field and the engine that drives solar activity, and it is a mystery, a thin layer of plasma that defies our best theories and challenges our understanding of how stars work. Above the tachocline, the physics changes once again. The plasma begins to move, to boil, to rise and fall in massive convection cells. We leave the realm of radiation and enter the realm of convection. We are approaching the surface, and with it, the visible face of the sun. Chapter 6: The Boiling Surface, Convection and the Photosphere. Above the tachocline, the sun becomes a boiling ocean. The convective zone extends from the base of the tachocline at about 70% of the solar radius, all the way to the visible surface of the sun, encompassing the outer 30% of the star's interior. This is a region of constant motion, where hot plasma rises from the depths, cools as it approaches the surface, and sinks back down to be reheated in an endless, turbulent cycle. The convective zone is the reason the sun has a surface at all. Without convection, the sun would be a smooth, featureless ball of glowing gas. With convection, the sun has texture, structure, and a dynamic, ever-changing appearance. Convection is a mode of energy transport that occurs when a fluid is heated from below. When the plasma at the base of the convective zone is heated by the energy diffusing up from the radiative zone, it expands and becomes less dense than the surrounding plasma. Being less dense, it is buoyant, and it begins to rise. As it rises, it carries energy with it, far more efficiently than radiation can. A rising blob of plasma can transport energy at speeds of hundreds of meters per second, compared to the glacial pace of radiative diffusion, which takes tens of thousands of years to move energy the same distance. The rising plasma does not travel in a straight line from the bottom to the top of the convective zone. It is turbulent, chaotic, and constantly interacting with other rising and falling blobs. The motion is organized into structures called convection cells, which come in a hierarchy of sizes. The smallest and most visible of these structures are called granules. Granules are the fundamental building blocks of solar convection, and they dominate the appearance of the sun's photosphere, the visible surface layer. A granule is a convection cell about 1,000 kilometers across, roughly the size of Texas or France. At the center of a granule, hot plasma is rising from below at speeds of about 1 to 2 kilometers per second. The plasma is about 400 degrees Celsius hotter than the surrounding material, and because it is hotter, it is brighter. When you look at the sun through a telescope equipped with the right filters and resolution, the photosphere appears grainy, like the surface of a pot of boiling oatmeal. Each bright grain is a granule, and the dark lanes between them are the cooler, sinking plasma. Granules are short-lived. They have a lifespan of only about 8 to 20 minutes. A granule is born when a rising plume of plasma reaches the surface and spreads out. It grows, expands, and then dies, either by fragmenting into smaller granules, merging with neighboring granules, or simply cooling and sinking back down. The surface of the sun is a constantly shifting, boiling landscape, with thousands of granules being born and dying every minute. It is a chaotic, turbulent environment, and it is one of the most beautiful sights in astronomy. Above the granules, both in size and in the hierarchy of convection, are structures called supergranules. Supergranules are enormous convection cells, about 30,000 to 35,000 kilometers across, more than twice the diameter of the Earth. They are not as bright or as easily visible as granules, but they can be detected by measuring the horizontal flow of plasma across the surface. Supergranules have much longer lifespans than granules, lasting about 20 to 24 hours. The convective flows in supergranules are also much faster, reaching speeds of about 400 meters per second. Supergranules play an important role in organizing the sun's magnetic field. The horizontal flows in supergranules sweep magnetic field lines to the edges of the cells, concentrating them into the dark lanes between supergranules. This is where magnetic flux tubes, the structures that eventually become sunspots, are assembled and stored. Between granules and supergranules, there may be another layer of convection called mesogranules, with sizes of about 5,000 to 10,000 kilometers and lifespans of a few hours. The existence and nature of mesogranules are still debated, and they may simply be the result of interactions between granules and supergranules rather than a distinct mode of convection. Regardless, the hierarchy of convection cells demonstrates that the convective zone is not a uniform, well-mixed layer. It is structured, with energy being transporting at multiple scales simultaneously. The top of the convective zone, the layer that we can actually see, is called the photosphere. The photosphere is not a solid surface. It is simply the layer of the sun from which photons can finally escape into space without being immediately reabsorbed. Below the photosphere, the plasma is so dense and opaque that photons are trapped, bouncing endlessly from particle to particle. Above the photosphere, the density drops sharply and photons can travel freely. The photosphere is defined as the layer where the optical depth, a measure of how opaque the plasma is, equals about 2/3. This is the layer from which most of the sun's light is emitted, and it is what we see when we look at the sun. The photosphere is about 500 kilometers thick, a tiny fraction of the sun's radius, and it has an average temperature of about 5,500 degrees Celsius. This might seem hot, and it is, but it is far cooler than the interior. The temperature drops steeply as you move outward through the photosphere. At the bottom of the photosphere, where it merges with the convective zone, the temperature is about 6,500 degrees. At the top, where the photosphere gives way to the chromosphere, the temperature has fallen to about 4,500 degrees. This temperature gradient is the reason for a phenomenon called limb darkening. Limb darkening is the observation that the sun appears brighter in the center of its disk and darker near the edges or limbs. This is not an optical illusion. It is a real effect caused by the temperature structure of the photosphere. When you look at the center of the sun's disk, your line of sight penetrates deeper into the photosphere, where the temperature is higher and the plasma is brighter. When you look near the edge of the disk, your line of sight passes through the cooler, upper layers of the photosphere at a shallow angle, and you see less of the hot, deep material. The result is that the limb appears dimmer. The photosphere is also where the energy that began its journey in the core, tens of thousands of years ago, finally escapes into space. The photons that reach the top of the photosphere are no longer gamma rays or X-rays. They have been downshifted through countless absorptions and re-emissions, and they are now visible light and infrared radiation, the gentle warmth and light that sustains life on Earth. The photosphere radiates energy at a rate of about 63 million watts per square meter, a staggering amount of energy that has been accumulating in the sun's interior for millennia. But the photosphere is not the end of the sun's atmosphere. Above it lies the chromosphere, a thin, reddish layer that can be seen during solar eclipses. And above that lies the corona, the sun's outer atmosphere, a place of searing heat and violent activity. The transition from the photosphere to the chromosphere and then to the corona is one of the most mysterious and counterintuitive phenomena in solar physics. As you move away from the sun's core, you expect the temperature to drop. And it does all the way up to the photosphere. But then, something strange happens. The temperature starts to rise again. The chromosphere is hotter than the photosphere, and the corona is hotter still, reaching temperatures of several million degrees Celsius, hundreds of times hotter than the photosphere below. This is the coronal heating problem, one of the greatest unsolved mysteries in astrophysics. How can the outer atmosphere of the sun be hotter than the surface when the source of energy is in the core, far below? It violates our intuition about heat flow. Heat should flow from hot regions to cold regions, not the other way around. And yet, the corona is blazing hot, and we do not fully understand why. The answer lies in the magnetic field, in the violent processes of magnetic reconnection, in shock waves and plasma instabilities that pump energy into the corona and heat it to millions of degrees. But the details are still being worked out, and the coronal heating problem remains one of the great challenges in solar physics. Understanding the corona, its temperature, its structure, and its violent eruptions is the next step in our journey. We must leave the surface and ascend into the outer atmosphere, where the sun's fury is unleashed and where the space weather that affects Earth is born. Chapter 7: The Corona Mystery and the Solar Wind. Above the photosphere, the sun's atmosphere becomes increasingly strange and hostile. The chromosphere, a thin reddish layer visible during solar eclipses, extends a few thousand kilometers above the photosphere. Its temperature is slightly higher than the photosphere, reaching about 20,000 degrees Celsius. But above the chromosphere lies something that defies all intuition. The corona, the sun's outer atmosphere, a ghostly halo of superheated plasma that extends millions of kilometers into space. The corona is visible during total solar eclipses as a pearly white glow surrounding the darkened disk of the moon. It is one of the most beautiful sights in nature, and it is also one of the most mysterious. The corona should not exist, at least not in the form we observe it. According to the basic principles of thermodynamics, heat flows from hot regions to cold regions. The core of the sun is 15 million degrees. The radiative zone is a few million degrees. The convective zone drops to about 2 million degrees at its base and cools further as you move outward. The photosphere, the visible surface, is a relatively cool 5,500 degrees Celsius. Logic says the temperature should continue to drop as you move farther from the energy source, and it does, briefly. The temperature drops to about 4,500 degrees at the top of the photosphere. But then, in a transition region only a few hundred kilometers thick, the temperature skyrockets. Within this narrow transition zone, the temperature jumps from 20,000 degrees in the chromosphere to over 1 million degrees in the corona, and in some regions, it can reach 2 to 3 million degrees or higher. This is an increase of more than 100-fold over a distance shorter than the width of Texas. It is as if you walked away from a campfire and the air got hotter the farther you moved. It violates our everyday experience of heat. This is the coronal heating problem, And despite decades of research, observations from spacecraft, and sophisticated computer simulations, we still do not have a complete answer to why the corona is so hot. The energy to heat the corona must ultimately come from below, from the convective zone and the photosphere. The question is how that energy is transporting upward and deposited into the tenuous corona. The plasma in the corona is incredibly thin, with a density about 1 billion times lower than the photosphere. If you took all the material in a cubic meter of the corona and compressed it to the density of air at sea level on Earth, it would fit into a thimble. This low density means the corona has very little thermal mass. It does not take much energy to heat it, but it also radiates and loses energy very quickly. To maintain the corona at millions of degrees, there must be a continuous influx of energy to replace what is lost. The leading candidate for coronal heating is magnetic reconnection, a process where magnetic field lines break and reconnect in new configurations, releasing enormous amounts of stored magnetic energy in the process. Magnetic reconnection is the same mechanism that powers solar flares and coronal mass ejections, but on a much smaller scale. The hypothesis is that the corona is heated by countless tiny reconnection events, each releasing energy equivalent to a nanoflare, an explosion far too small to be detected individually, but collectively capable of heating the entire corona. The theory, first proposed by physicist Eugene Parker in the 1980s, suggests that the magnetic field in the corona is constantly being braided and twisted by the turbulent motion of the photosphere below. As the field lines are stressed and tangled, they form thin current sheets, regions where the magnetic field changes direction very rapidly over a short distance. When the stress becomes too great, the field lines snap and reconnect, converting magnetic energy into heat and kinetic energy. Each nanoflare releases about 10 to the 24th power ergs of energy, roughly 1 million times less than a typical solar flare. But there are billions of these events happening constantly across the entire corona, and together they may provide enough energy to keep the corona blazing hot. Observations from spacecraft like the Solar Dynamics Observatory have provided tantalizing evidence for nanoflares, detecting small, rapid brightenings in the extreme ultraviolet emissions from the corona. But detecting individual nanoflares remains a challenge because they are so small and so short-lived. Another heating mechanism that has been proposed involves Photon waves, oscillations in the magnetic field that propagate along the field lines like waves on a string. These waves, generated by the turbulent motion of the photosphere, can carry energy upward into the corona. When the waves steepen into shocks or undergo dissipation through turbulence, they release their energy as heat. Recent observations from the Parker Solar Probe, a spacecraft that has flown closer to the Sun than any human-made object, have detected evidence of strong Photon wave activity in the corona, supporting this theory. The Parker Solar Probe has also discovered an entirely new phenomenon in the solar wind, magnetic switchbacks. These are sudden, brief reversals in the direction of the magnetic field embedded in the solar wind. During a switchback, the magnetic field flips around and points almost directly back at the Sun, the opposite of its usual direction. These reversals last anywhere from a few seconds to several minutes and are incredibly common in the inner solar wind, closer to the Sun. The origin of switchbacks is still being investigated, but recent research suggests they may be connected to the supergranular flows at the photosphere, the large-scale convection cells that organize the magnetic field at the surface. Switchbacks may represent jets or eruptions of magnetic flux from the photosphere that get twisted and kinked as they rise through the corona. These magnetic kinks then propagate outward with the solar wind. If this interpretation is correct, switchbacks are a direct signature of the violent, dynamic processes happening at the base of the corona, and they may play a role in accelerating and heating the solar wind itself. The corona is not just hot, it is also the source of the solar wind, a continuous stream of charged particles that flows out from the Sun in all directions at speeds ranging from 300 to 800 kilometers per second. The solar wind was predicted theoretically by Eugene Parker in 1958, decades before it was directly observed. Parker realized that the corona is so hot that it cannot be in hydrostatic equilibrium. The thermal pressure of the corona is too high for gravity to contain it. The corona must be expanding, blowing off into space as a supersonic wind. This was a radical idea at the time, but observations from early spacecraft, including Mariner 2 in 1962, confirmed that the solar wind exists and flows past Earth at high speed. The solar wind comes in two main varieties: fast wind and slow wind. Fast wind originates from coronal holes, regions of the corona where the magnetic field lines are open, extending outward into interplanetary space rather than looping back to the sun. Coronal holes appear as dark regions in extreme ultraviolet images of the sun because the plasma in these regions is cooler and less dense than the surrounding corona. The open magnetic field lines allow plasma to escape easily, and the fast wind streams out at speeds of about 700 to 800 kilometers per second. Fast wind is relatively smooth and steady. Its composition is similar to the photosphere, with only a slight enhancement of low first ionization potential elements, a phenomenon known as the FIP effect. The temperature of the fast wind, as inferred from the charged states of the ions, suggests a freezing-in temperature of about 1 million degrees, indicating that the fast wind originates from relatively cool regions of the corona. Slow wind, on the other hand, is more variable and more mysterious. It flows at speeds of about 300 to 500 kilometers per second and appears to originate from the boundaries of coronal streamers, helmet-shaped magnetic structures that close back on themselves. Slow wind has a more complex composition, with a stronger FIP effect and a higher freezing-in temperature, suggesting it comes from hotter, more magnetically complex regions of the corona. The slow wind is also more turbulent and variable, with fluctuations in speed, density, and magnetic field strength. The exact mechanism that produces slow wind is still debated, but it may involve the periodic release of plasma from the tips of streamers or the interaction between open and closed magnetic field lines at the streamer boundaries. The solar wind carries the sun's magnetic field with it into interplanetary space. Because the sun is rotating, the magnetic field lines embedded in the solar wind are twisted into a spiral pattern known as the Parker spiral. Near the sun, the field lines point radially outward, but as the solar wind flows away from the sun, the field lines are dragged along by the wind, while their footprints at the sun's surface are carried around by the sun's rotation. The result is a spiral shape, like water spraying from a rotating garden sprinkler. At Earth's orbit, the magnetic field lines are tilted at about 45 degrees to the radial direction. The solar wind does not flow forever, at some distance from the sun. Estimated to be about 120 astronomical units, or 120 times the Earth-Sun distance, the solar wind slows down and collides with the interstellar medium, the thin gas and dust that fills the space between stars. This boundary is called the heliopause, and it marks the edge of the sun's influence, the boundary of the heliosphere. The Voyager 1 spacecraft crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. Measurements from these spacecraft have shown that the heliopause is a dynamic, turbulent boundary, buffeted by variations in the solar wind and the external pressure of the interstellar medium. The corona and the solar wind are not static. They are constantly changing, driven by the rise and fall of the sun's magnetic activity. This activity follows an 11-year cycle, known as the solar cycle, during which the number of sunspots, solar flares, and coronal mass ejections waxes and wanes. Understanding this cycle, its causes, and its consequences for Earth is the next step in our journey through the story of the sun. Chapter 8: The Magnetic Cycle, Sunspots and Polarity Flips. The sun is not a constant, unchanging star. It breathes, it cycles. Every 11 years, its magnetic activity rises from a quiet minimum to a furious maximum, then falls again to quiet, only to begin the cycle anew. This is the solar cycle, also known as the sunspot cycle, and it is one of the most prominent and well-documented patterns in solar physics. The cycle has been observed for more than 400 years, ever since Galileo first pointed a telescope at the sun and noticed dark spots moving across its surface. These spots were not flaws in his instrument or clouds in the atmosphere. They were real features on the sun itself, and their number varied over time in a predictable pattern. Sunspots are regions of the photosphere where the magnetic field is extraordinarily strong, thousands of times stronger than the average magnetic field at the sun's surface. A typical sunspot has a magnetic field strength of about 2,000 to 3,000 Gauss, with some reaching as high as 4,000 Gauss or more. To put this in perspective, the Earth's magnetic field at the surface is only about 0.5 Gauss, and a strong refrigerator magnet is about 100 Gauss. The magnetic field in a sunspot is so strong that it suppresses the convection of plasma beneath the surface, preventing hot material from rising. Without the constant supply of heat from below, the sunspot cools down relative to the surrounding photosphere, making it appear dark. A sunspot typically consists of two regions, the umbra and the penumbra. The umbra is the dark central region, where the magnetic field is nearly vertical and the field strength is highest. The temperature of the umbra is about 3,000 to 4,500 degrees Celsius, roughly 2,000 degrees cooler than the surrounding photosphere. This temperature difference is enough to make the umbra appear black by contrast, though if you could see the umbra in isolation, it would still glow brightly. Surrounding the umbra is the penumbra, a lighter, striated region where the magnetic field is inclined at an angle to the surface. The penumbra has a complex structure, with bright and dark filaments radiating outward from the umbra. The magnetic field in the penumbra is weaker than in the umbra, typically around 1,000 to 2,000 Gauss. Sunspots can be enormous. A large sunspot can be several times the diameter of the Earth, and the largest sunspot groups can stretch for hundreds of thousands of kilometers across the sun's surface. Sunspots usually appear in pairs or groups, with one spot having a north magnetic polarity and the other having a south polarity. These pairs are the footprints of massive magnetic loops that arch high into the corona, trapping hot plasma in their grip. Sunspots can last for days, weeks, or even months, depending on their size and the strength of the underlying magnetic field. As they persist, the sun's rotation carries them across the visible disk, from the eastern limb to the western limb, over the course of about 2 weeks. The number of sunspots visible on the sun varies dramatically over the course of the solar cycle. At solar minimum, the sun can go days or even weeks without a single visible sunspot. The photosphere appears smooth and featureless. At solar maximum, the sun can be covered with dozens of sunspots and active regions, giving it a mottled, chaotic appearance. The transition from minimum to maximum takes about 4 to 5 years, and the decline from maximum back to minimum takes another 6 to 7 years. The total cycle length averages about 11 years, though individual cycles can be as short as 9 years or as long as 14 years. But the solar cycle is not just an 11-year phenomenon. It is actually a 22-year cycle when you account for the polarity of the magnetic field. At the beginning of a cycle, sunspots appear at mid-latitudes, around 30 to 40 degrees north and south of the equator. In the northern hemisphere, the leading spot in a sunspot pair, the one that rotates into view first, might have a north magnetic polarity, while the trailing spot has a south polarity. In the southern hemisphere, the pattern is reversed. The leading spot has a south polarity and the trailing spot has a north polarity. As the cycle progresses, new sunspots appear at progressively lower latitudes, creeping toward the equator. By the end of the cycle, sunspots are appearing close to the equator at latitudes of only 5 to 10 degrees. Then the polarity flips. At the start of the next 11-year cycle, sunspots reappear at mid-latitudes, but now the polarities are reversed. What was north is now south, and what was south is now north. It takes 2 11-year cycles, a total of 22 years, for the sun's magnetic field to return to its original configuration. This 22-year pattern is known as the Hale cycle, named after astronomer George Ellery Hale, who discovered the magnetic nature of sunspots in 1908. When you plot the latitude of sunspots as a function of time over multiple solar cycles, you get a distinctive pattern known as the butterfly diagram, because the shapes resemble the wings of a butterfly. The diagram shows sunspots starting at high latitudes and migrating toward the equator as the cycle progresses, with a new cycle beginning at high latitudes before the previous cycle has completely ended at the equator. This overlap creates a period of several years where sunspots from two different cycles, with opposite magnetic polarities, coexist on the Sun. The solar cycle is driven by the solar dynamo, the same process we discussed in the context of the tachocline. The dynamo generates the Sun's magnetic field through the interaction of differential rotation, convection, and magnetic buoyancy. The toroidal magnetic field created in the tachocline becomes unstable and rises through the convective zone in the form of magnetic flux tubes. When these tubes reach the surface, they pierce the photosphere and create sunspot pairs. The magnetic field inhibits convection, causing the sunspots to be cooler and darker than their surroundings. But the solar cycle is not perfectly regular. Some cycles are stronger than others, with more sunspots and more intense magnetic activity, and occasionally the cycle fails almost entirely. Between 1645 and 1715, a period known as the Maunder minimum, sunspots virtually disappeared. Observers reported seeing only a handful of sunspots over the course of 70 years, a period that normally would have seen thousands. The Maunder minimum coincided with the coldest period of the Little Ice Age in Europe, when winters were harsh, rivers froze that had never frozen before, and crop failures led to famine. The connection between the Maunder minimum and the Little Ice Age is still debated, but it is clear that the Sun's magnetic activity was severely suppressed during this time. The dynamo did not stop entirely. Evidence from cosmogenic isotopes like carbon-14 and beryllium-10 suggests that the 11-year and 22-year cycles continued, but at a much reduced amplitude. The sunspot formation threshold was simply not reached most of the time. Why the dynamo entered this suppressed state, and why it recovered in the early 18th century, remains one of the great mysteries of solar physics. The Maunder minimum is not unique. There have been other grand minima in the Sun's history, including the Spora minimum in the 15th century and the Dalton minimum in the early 19th century. These periods remind us that the Sun is a variable star, and its behavior over decades and centuries can have profound effects on Earth's climate and environment. Understanding the solar cycle, predicting its strength, and preparing for periods of high activity is not just an academic exercise. It is a matter of practical importance for our technological civilization, which is increasingly vulnerable to the Sun's magnetic fury. The most violent manifestations of solar activity, solar flares and coronal mass ejections, are the subject of the next chapter, where we will explore the moments when the Sun lashes out and attacks. Chapter 9: The Carrington Event, when the Sun attacked. On the morning of September 1st, 1859, Richard Carrington, a wealthy English brewer and amateur astronomer, was doing what he did nearly every clear day, observing the Sun through his telescope at his private observatory in Redhill, Surrey. He was tracking a large group of sunspots, carefully recording their positions and shapes on paper. It was routine work, the kind of patient observation that had occupied astronomers for more than 2 centuries since Galileo first turned a telescope skyward. But at 11:18 in the morning, something extraordinary happened. 2 intensely bright patches of white light appeared within the sunspot group. They were so brilliant that they were visible even against the blinding background of the Sun's photosphere. Carrington watched in astonishment as the bright patches moved, separated, and then faded away over the course of about 5 minutes. Unknown to Carrington, he had just witnessed the first recorded observation of a solar flare, a massive explosion on the surface of the Sun. At almost the same moment, 20 miles away in London, another astronomer named Richard Hodgson independently observed the same event. Both men immediately suspected that what they had seen was important, though neither could have predicted the chaos that was about to unfold on Earth. Within 17 hours, the fastest coronal mass ejection ever recorded slammed into Earth's magnetic field with devastating force. The Carrington event, as it came to be known, remains the most intense geomagnetic storm in recorded history. The effects were immediate and spectacular. Telegraph systems, the cutting-edge technology of the Victorian era, went haywire across Europe and North America. Telegraph operators reported receiving electrical shocks through their equipment, severe enough to knock them off their chairs. Sparks flew from telegraph keys, setting papers on fire. In some cases, the induced currents were so strong that telegraph operators disconnected their batteries and found they could continue sending messages using only the current induced by the geomagnetic storm itself. The technology that connected the world had become, temporarily, a weapon. But the most spectacular effect of the Carrington event was the auroras. Normally confined to the polar regions, the aurora borealis and aurora australis spread to latitudes that had never seen them before and have rarely seen them since. On the night of September 1st and 2nd, brilliant auroras were visible as far south as the Caribbean, Hawaii, and Colombia. In the Rocky Mountains, the glow was so bright that miners woke up at 1:00 in the morning and began preparing breakfast, convinced that dawn had arrived. In New England, people could read newspapers outdoors at midnight by the light of the auroras alone. The sky was painted in vivid reds, greens, and purples, shifting and dancing in ways that terrified those who had never seen such a phenomenon. The auroras were described in contemporary accounts as curtains of fire, blood-red skies, and celestial fireworks. One observer in Boston wrote that the sky looked as though the entire northern horizon was on fire, with flames rising high into the heavens. In Armagh, Ireland, observatory records show that auroras were observed over 5 nights between August 28th and September 4th, with the displays on September 2nd and 3rd described as evidently strong and filling the sky. The fact that auroras were visible at such low latitudes, reaching as far south as 18 degrees geomagnetic latitude, indicates that the geomagnetic storm was extraordinarily intense, far stronger than anything experienced in the modern era. The scientific instruments of the time, primitive by today's standards, recorded the magnetic disturbance. Magnetometers in observatories around the world went completely off scale, their needles swinging wildly or becoming pegged at the limits of their range. The disturbance to Earth's magnetic field was so severe that it created what scientists now call geomagnetically induced currents, or GICs, massive electrical currents flowing through the ground and through any conductive infrastructure, like telegraph wires. To understand what happened during the Carrington event, we must understand the physics of coronal mass ejections and their interaction with Earth's magnetosphere. A coronal mass ejection, or CME, is a massive eruption of plasma and magnetic field from the sun's corona. CMEs are born when the magnetic field in the corona becomes twisted and stressed beyond the breaking point, usually in active regions associated with sunspots. When the field lines reconnect, they release an enormous amount of stored magnetic energy. The plasma that was trapped in the magnetic loops is suddenly freed and flung into space at speeds that can range from a few hundred kilometers per second to more than 3,000 kilometers per second. A typical CME ejects between 1 billion and 10 billion tons of plasma into interplanetary space. The fastest CMEs can traverse the 150 million kilometers from the Sun to Earth in as little as 15 to 18 hours. The CME that struck Earth during the Carrington event was exceptionally fast, arriving in only about 17 hours, suggesting a speed of well over 2,000 kilometers per second. This was no ordinary solar storm. It was a direct hit from one of the most powerful eruptions the Sun is capable of producing. When a CME reaches Earth, it does not simply slam into the planet like a projectile hitting a wall. Instead, it interacts with Earth's magnetic field, the magnetosphere, a protective bubble that shields us from the constant barrage of the solar wind. The interaction depends critically on the orientation of the magnetic field embedded in the CME. If the CME's magnetic field is aligned in the same direction as Earth's field, the two fields will tend to repel each other, and the CME will slide around the magnetosphere, causing only minor disturbances. But if the CME's magnetic field is aligned opposite to Earth's field, a process called magnetic reconnection occurs. Magnetic reconnection is a violent process where oppositely directed magnetic field lines break and reconnect in new configurations, releasing enormous amounts of energy. When this happens on the day side of Earth's magnetosphere, it allows the plasma from the CME to penetrate deep into the magnetosphere, compressing it and injecting vast amounts of energy. This energy is then dumped into the upper atmosphere, primarily at high latitudes near the magnetic poles, where the field lines converge. The result is a geomagnetic storm, characterized by intense auroras, fluctuations in Earth's magnetic field, and the induction of electrical currents in the ground and in long conductors like power lines and pipelines. The Carrington event was a perfect storm in every sense. The CME was exceptionally fast, exceptionally massive, and its magnetic field was oriented in exactly the wrong direction, allowing maximum energy transfer to Earth's magnetosphere. The geomagnetic disturbance lasted for days, with the most intense phase occurring on the night of September 1st through 2nd. The energy dumped into the magnetosphere was sufficient to drive auroras to the equator and to induce currents strong enough to disrupt the only electrical infrastructure that existed at the time, the telegraph network. If the Carrington event had occurred in 1859, it would have been a curiosity, a spectacular natural light show that disrupted a nascent technology. But if an identical event were to occur today, the consequences would be catastrophic. Modern civilization is utterly dependent on electrical power, and the power grid is exquisitely vulnerable to geomagnetically induced currents. High-voltage transformers, the backbone of the grid, are designed to handle alternating current, not the direct current that GICs inject into the system. When a transformer is subjected to a large DC current, its magnetic core becomes saturated, causing it to overheat, generate harmonics, and consume excessive reactive power. In the worst case, the transformer can suffer permanent damage, its insulation breaking down and its internal components fusing together. Large power transformers are custom-built, incredibly expensive, and take months or even years to manufacture and replace. A Carrington-level event today could destroy hundreds of transformers simultaneously across multiple continents. The result would be widespread, long-duration blackouts affecting hundreds of millions of people. Without electricity, water treatment plants would fail, hospitals would run out of backup power, communication networks would collapse, and supply chains would grind to a halt. The economic damage would be measured in trillions of dollars, and the societal disruption could last for years. We have already seen glimpses of what a major geomagnetic storm can do to modern infrastructure. On March 13, 1989, a geomagnetic storm far weaker than the Carrington event caused the collapse of the entire Quebec power grid in less than 2 minutes. At 2:44 in the morning, geomagnetically induced currents caused 7 protective relay schemes to actuate almost simultaneously. The grid became unstable, and the automatic protection systems, designed to prevent damage to transformers, shut down the entire network. 6 million people were plunged into darkness. Power was not fully restored for 12 hours. The storm also caused a transformer at a nuclear power plant in New Jersey to fail, and it damaged transformers in the United Kingdom. The Quebec blackout was caused by a storm with a disturbance storm time index, or DST, of about -600 nanoteslas, a measure of the intensity of the geomagnetic disturbance. The Carrington event is estimated to have had a DST of at least -850 nanoteslas, and possibly as low as -1,700 nanoteslas, more than twice as intense as the 1989 storm. If the Carrington event were to repeat today, it would not just knock out Quebec, it would knock out grids across North America, Europe, and Asia. But geomagnetic storms are not the only threat from solar activity. Solar flares, the initial explosions that often precede CMEs, emit intense bursts of X-rays and ultraviolet radiation that travel at the speed of light and arrive at Earth in just 8 minutes. These high-energy photons do not penetrate to the surface. They are absorbed in the upper atmosphere, in the ionosphere. But in the process, they cause dramatic changes to the ionosphere's structure, increasing its ionization and disrupting radio communications. High-frequency radio, used by aircraft for long-distance communication, can be completely blacked out during a major flare. GPS signals, which rely on precise timing and propagation through the ionosphere, can be degraded or rendered useless. Satellites in low Earth orbit experience increased atmospheric drag as the upper atmosphere heats and expands, shortening their orbital lifetimes and increasing the risk of collisions. We have been lucky. Since the dawn of the electrical age, we have not experienced a Carrington-level event, but we came terrifyingly close in July 2012, when the Sun unleashed one of the most powerful CMEs ever recorded. On July 23, 2012, a massive eruption tore through the solar corona and blasted into space at a speed of approximately 3,000 kilometers per second, among the fastest CMEs ever measured. The CME carried a magnetic field configuration that would have caused severe magnetic reconnection with Earth's magnetosphere. By every measure, it was a Carrington-class event. But we were saved by timing. The eruption occurred on the far side of the Sun, directed away from Earth toward a longitude of about 125 degrees west. Instead of hitting Earth, the CME struck the Stairway spacecraft, a solar observatory orbiting the Sun ahead of Earth. Stairway's instruments measured the full fury of the storm and survived to send back data. The measurements showed that the CME reached the spacecraft in only 18 to 19 hours, an astonishingly short transit time. Scientists who analyzed the event concluded that if the CME had been directed at Earth, it would have caused damage on a scale not seen since 1859, potentially knocking modern civilization back to the 18th century. The July 2012 event was a wake-up call. It demonstrated that the Sun is still capable of producing extreme events, and it is only a matter of time before Earth is in the line of fire. The question is not if, but when the next Carrington event will occur, and when it does, will we be ready? Chapter 10: The Modern Threat, the Inevitable Blackout. The Carrington event happened in 1859, a time when the most advanced technology was the telegraph. The July 2012 near-miss happened in an era of smartphones, GPS, and the Internet. The difference between these two epochs is everything. In 1859, the world was connected by copper wires carrying simple electrical pulses. Today, the world is connected by a vast, fragile web of electrical grids, communication satellites, fiber optic cables, and data centers. Every aspect of modern life, from the water supply to the food distribution system, from banking to healthcare, depends on the continuous, uninterrupted flow of electricity. We have built a civilization on the assumption that the Sun will remain calm. But the Sun is not calm. It is a variable, active star, and it is overdue for another tantrum. The threat from solar activity is not hypothetical. It is real, it is growing, and it is inevitable. Every 11 years, the Sun goes through a cycle of magnetic activity, and during the peak of each cycle, the probability of a major solar storm increases. But even during solar minimum, when the Sun is relatively quiet, large eruptions can occur. The Carrington event itself occurred during a relatively modest solar cycle, not even one of the strongest on record. This tells us that the Sun is capable of producing extreme events at any time, regardless of where we are in the solar cycle. The vulnerability of the modern world to solar storms was first recognized in the 1970s, when satellites began to experience anomalies during periods of high solar activity. Engineers noticed that satellites would suffer temporary malfunctions, memory errors, and sometimes permanent damage when exposed to the intense radiation and charged particles from solar flares and CMEs. As our reliance on space-based technology grew, so did the awareness of the threat. But it was not until the Quebec blackout of 1989 that the power industry began to take geomagnetic storms seriously. The Quebec event revealed a fundamental weakness in the design of modern power grids. The grid is optimized for efficiency, with long transmission lines carrying power over vast distances. These long lines act as antennas, picking up the fluctuating magnetic fields during a geomagnetic storm and converting them into geomagnetically induced currents that flow into transformers. The longer the transmission line, the larger the induced current. Quebec's grid, with its long north-south transmission lines stretching from hydroelectric dams in the north to population centers in the south, was particularly vulnerable. The Canadian Shield, a vast expanse of highly resistive rock underlying much of eastern Canada, also contributed to the problem by providing a poor ground return path, forcing the currents to flow through the power lines. Since 1989, power companies have implemented some protective measures. Transformers are monitored for signs of overheating and excessive reactive power consumption. Capacitor banks are installed to compensate for the reactive power losses during a storm. Some utilities have installed blocking devices to prevent DC currents from entering transformers, but these measures are patchwork, inconsistent, and largely voluntary. There is no global, coordinated strategy to protect the grid from a Carrington-level event. Many transformers, especially in older parts of the grid, remain unprotected, and the sheer scale of the problem is daunting. A severe geomagnetic storm would affect multiple grids simultaneously across entire continents, overwhelming the ability of utilities to respond. The threat extends beyond the power grid. Communications satellites in geostationary orbit, which provide television, internet, and telephone services, are exposed to the full force of a CME. The energetic particles can penetrate the satellite's shielding, causing damage to electronics, solar panels, and sensors. During the March 1989 storm, a communications satellite temporarily lost contact with the ground, and during a storm in 1998, the Galaxy IV satellite failed completely, knocking out pager service for millions of people in North America. GPS satellites, which operate in medium Earth orbit, are also vulnerable. The ionospheric disturbances caused by solar flares can degrade the accuracy of GPS signals, making them unreliable for navigation, surveying, and precision agriculture. In a severe storm, GPS could be rendered useless for days. Astronauts in space face a different kind of threat. Solar flares emit high-energy protons that can penetrate spacecraft and spacesuits, delivering dangerous doses of radiation. During a major solar proton event, astronauts on the International Space Station must take shelter in the most heavily shielded modules to avoid exceeding their radiation exposure limits. For astronauts on a mission to the Moon or Mars, where there is no planetary magnetic field to provide protection, a major solar storm could be lethal. NASA's plans for deep space exploration must account for this risk, either by designing heavily shielded spacecraft or by timing missions to avoid periods of high solar activity. The airline industry is also affected. High-frequency radio, used for communication with aircraft flying over the polar regions where satellite coverage is sparse, can be completely blacked out during a solar flare. Flights must be rerouted to lower latitudes or delayed until communications are restored. The radiation dose received by passengers and crew also increases during a solar storm, though it remains below dangerous levels for occasional flyers. However, frequent flyers and flight crew can accumulate significant doses over their careers, and airlines are required to monitor and limit exposure. Beyond the immediate technological impacts, there are cascading effects that could cripple society. Without electricity, water treatment plants cannot operate, pumps fail, and water pressure drops. Within hours, tap water becomes unsafe to drink, food spoils in refrigerators, gas stations cannot pump fuel, ATMs do not work, credit card systems go offline, hospitals exhaust their diesel backup generators within days, elevators stop, heating and cooling systems fail. In winter, people freeze. In summer, they suffer heat stroke. The elderly and the sick are the first to die. Law and order begin to break down as desperation sets in. This is not science fiction. This is the scenario that emergency planners have wargamed in government exercises. A 2008 report by the National Academy of Sciences estimated that a Carrington-level event could cause between $1 to $2 trillion in damage in the first year alone, with full recovery taking 4 to 10 years. The economic disruption would be global. Manufacturing would halt. Supply chains would collapse. International trade would seize up. The event would trigger a worldwide recession, possibly a depression. So why has nothing been done? The answer is a combination of inertia, cost, and the tragedy of the commons. Hardening the power grid against geomagnetic storms would cost tens of billions of dollars. Utilities are reluctant to make such investments when the return on investment is uncertain and the probability of a major storm in any given year is low. Governments are reluctant to mandate expensive upgrades when the political will is lacking and the threat seems abstract and distant. There is a pervasive sense that it won't happen to us, or we'll deal with it when it happens. But by the time it happens, it will be too late. The good news is that we are not entirely blind. We have early warning systems. Spacecraft like the Solar and Heliospheric Observatory, or SOHO, and the Solar Dynamics Observatory, or SDO, monitor the sun continuously, watching for flares and CMEs. When a CME is detected, its speed and direction can be estimated, allowing forecasters to predict whether it will hit Earth, and if so, when. This provides anywhere from 15 hours to several days of warning, depending on the speed of the CME. The warning is relayed to power companies, satellite operators, and government agencies, giving them time to take protective measures. But warning is not the same as protection. Even with advance notice, there is little that can be done to prevent a major geomagnetic storm from causing damage. Power grids can be partially shut down to reduce the load on transformers, but this itself causes blackouts and economic disruption. Satellites can be put into safe mode, but they remain vulnerable to the energetic particles. Astronauts can take shelter, but they cannot stay there indefinitely. The warning buys time, but it does not eliminate the threat. What is needed is a comprehensive, long-term strategy to harden critical infrastructure against space weather. This includes installing blocking devices to protect transformers, building redundancy into the grid so that the failure of one component does not cascade into a widespread blackout, and developing rapid response teams that can replace damaged transformers quickly. It also means improving our understanding of space weather through better models and more observations. The Parker Solar Probe, which has flown closer to the Sun than any previous spacecraft, is providing unprecedented data on the solar wind and the processes that drive CMEs and flares. Future missions will continue to improve our ability to forecast space weather and to understand the Sun's behavior. But ultimately, the question is not whether another Carrington event will occur. It is when. The Sun is a star, and stars are not stable. They flare, they erupt, they vary. We have been living through a period of relative solar calm, a lull between storms, but the July 2012 event showed us that the Sun has not lost its power. The next time we may not be so lucky. The next time the CME may be aimed directly at Earth. And when that happens, the lights will go out, and modern civilization will face its greatest test. Chapter 11, The Great Brightening, the Death of Earth 1 billion years. The Sun is killing the Earth right now. It is a slow, inexorable process, one that operates on timescales so vast that it is invisible to human perception. But it is happening. Every billion years, the Sun gets about 10% brighter. This brightening is not caused by an increase in the fusion rate in the core, at least not directly. It is caused by the gradual accumulation of helium in the core, the ash left behind by billions of years of burning hydrogen. As helium builds up, the core becomes denser. To maintain the pressure needed to support the overlying layers against gravity, the core must get hotter. Hotter cores fuse hydrogen faster, and faster fusion produces more energy. The result is that the Sun's luminosity, the total amount of energy it radiates into space, increases slowly but steadily over time. When the Sun first formed 4.6 billion years ago, it was about 30% dimmer than it is today. This is the faint young Sun that we discussed earlier, the star that should have left the early Earth frozen but somehow did not. Over the intervening eons, the Sun has been steadily growing brighter. A billion years ago, it was about 9% dimmer than it is now. A billion years from now, it will be about 10% brighter than it is today. This might sound like a small change, but for a planet like Earth, perched in the narrow habitable zone where liquid water can exist, it is a death sentence. The additional energy from the Sun will heat the Earth's surface and atmosphere. As temperatures rise, more water will evaporate from the oceans. Water vapor is a greenhouse gas, far more potent than carbon dioxide. The additional water vapor will trap more heat, causing more evaporation in a vicious, self-reinforcing cycle. This is called the moist greenhouse effect, and it will transform Earth into a hellish sauna. The oceans will not boil immediately, but they will begin to evaporate, slowly at first. then faster and faster as the positive feedback loop accelerates. At the same time, the increased temperatures will accelerate the weathering of rocks. On Earth today, carbon dioxide is regulated by a geological thermostat. When temperatures rise, weathering increases, pulling more carbon dioxide out of the atmosphere and locking it away in carbonate rocks. This cools the planet. When temperatures fall, weathering slows, and volcanic outgassing replenishes the carbon dioxide, warming the planet. This feedback loop has kept Earth's climate relatively stable for billions of years, despite the increasing brightness of the sun. But there is a limit to how much this thermostat can compensate. As the sun gets brighter, the thermostat will work harder and harder to cool the planet, pulling more and more carbon dioxide out of the atmosphere. Eventually, about 500 million to 1 billion years from now, the carbon dioxide concentration will drop so low that plants can no longer photosynthesize. Without photosynthesis, the biosphere will collapse. Plants will die first, followed by the herbivores that depend on them, and then the carnivores. The oxygen in the atmosphere, which is produced almost entirely by photosynthesis, will begin to decline. Within a few million years, complex life will be extinct. Only simple microbes, clinging to life in deep underground aquifers or in extreme environments, will remain. But the planet itself will continue to suffer. Without the carbon dioxide sink provided by photosynthesis and the carbonate-silicate cycle, the greenhouse effect will accelerate unchecked. The surface temperature will rise above the boiling point of water. The oceans will evaporate completely, turning Earth into a steam bath. The water vapor in the atmosphere will be broken apart by ultraviolet radiation from the sun. The hydrogen will escape into space, while the oxygen will oxidize the rocks on the surface. Earth will lose its oceans permanently and irreversibly. This process is already well underway on Venus, which may have had oceans billions of years ago before a runaway greenhouse effect turned it into the toxic, scorched wasteland it is today. Computer models suggest that Earth will reach this runaway greenhouse state in about 1 to 1.5 billion years. Some models suggest it could happen sooner, in as little as 500 million years, depending on how quickly the sun brightens and how the carbon cycle responds. Other models suggest it could take as long as 2 billion years. But the end result is the same. Earth will lose its water, its atmosphere will become dominated by carbon dioxide and nitrogen, and the surface temperature will soar to several hundred degrees Celsius. The planet will be uninhabitable, not just for humans, but for any form of life that we would recognize. This is not the death of the sun. The sun will still be a stable main-sequence star, happily fusing hydrogen into helium in its core. It will continue to do so for another 4 to 5 billion years after Earth becomes uninhabitable. But for Earth, and for any life that might exist on it, the brightening of the sun is a slow apocalypse, a death by 1,000 cuts that is as certain as it is gradual. The biosphere that has flourished for 3.8 billion years, that survived mass extinctions, ice ages, and asteroid impacts, will finally succumb to the relentless increase in solar output. The Earth will become a dead, dry, lifeless rock, a monument to what once was. And yet, even this is not the end of the story. The sun is not finished with the Earth. Long after the oceans have boiled away, long after the last microbe has perished, the sun will continue its inexorable evolution toward its final fate. And that fate will be far more dramatic, far more violent than anything we have discussed so far. The sun will leave the main sequence. It will swell into a red giant, a bloated, dying star hundreds of times its current size, and it will consume the inner planets, one by one. That is the next chapter of our story, the chapter where the sun becomes a monster and devours its own children. Chapter 12, The Red Giant, Consuming the Inner Worlds. 5 billion years from now, the sun will run out of hydrogen fuel in its core. For nearly 10 billion years, the core has been fusing hydrogen into helium, maintaining a stable balance between gravity and the outward pressure of fusion. But the supply of hydrogen is not infinite. As the core is depleted, the fusion reactions slow down and eventually stop. The energy source that has kept the sun shining for eons will be extinguished. The war between gravity and radiation pressure which has been locked in a perfect stalemate for billions of years, will tip decisively in favor of gravity. The core will collapse. But the sun will not die quietly. It will not fade into darkness. Instead, it will undergo a transformation so dramatic, so violent, and so catastrophic that it will fundamentally change the structure of the entire solar system. The sun will become a red giant, and in the process, it will likely destroy Mercury, Venus, and possibly even Earth. The sequence of events leading to the red giant phase is complex but inexorable. When the core runs out of hydrogen, fusion ceases, and the core begins to contract under its own weight. As it contracts, gravitational potential energy is converted into heat, and the core temperature rises. The rising temperature heats the layer of hydrogen just outside the core, a shell that still contains unburned hydrogen fuel. Eventually, the temperature in this shell rises high enough for hydrogen fusion to ignite. The sun transitions from core hydrogen burning to shell hydrogen burning. This is called the hydrogen shell burning stage, and it changes everything. The hydrogen shell generates energy faster than the original main sequence core ever did. This is because the shell is surrounding a shrinking, heating helium core, and the temperature in the shell is higher than the temperature in the main sequence core ever was. The increased energy production causes the sun's outer envelope to expand. Paradoxically, even though the core is contracting and heating, the outer layers of the star expand and cool. The sun's radius begins to grow. As the shell continues to burn, the helium core continues to shrink, and the temperature continues to rise. The shell burns hotter and hotter, producing more and more energy. The outer envelope expands further and further. The sun's luminosity increases dramatically, climbing to hundreds and eventually thousands of times its current value. At the same time, the surface temperature drops from the current 5,500 degrees Celsius to around 3,000 to 4,000 degrees. The cooler surface temperature gives the star a reddish color, hence the name red giant. The expansion is staggering in scale. At the peak of the red giant phase, the sun's radius will grow to somewhere between 100 and 250 times its current size, depending on the exact details of the mass loss and the evolution. At a minimum, the sun will extend out to at least the orbit of Venus and possibly beyond the orbit of Earth. The photosphere, the visible surface of the sun, will loom in the sky like an impossibly vast wall of fire, filling the entire horizon and beyond. If any remnants of humanity still exist on Earth at this point, they will witness the end of the world in the most literal sense imaginable. Mercury, the innermost planet, does not stand a chance. Its orbit is at 0.39 astronomical units, or 58 million kilometers from the Sun. When the Sun expands to 100 times its current radius, the photosphere will extend to about 70 million kilometers, far beyond Mercury's orbit. Mercury will be swallowed whole. The planet will spiral inward as it encounters the tenuous, but still significant atmosphere of the expanding Sun, experiencing drag that will decay its orbit. Within a relatively short time, geologically speaking, Mercury will plunge into the deeper layers of the Sun and vaporize completely. The planet that has circled the Sun for 4.5 billion years, that survived the Titori winds and countless asteroid impacts, will be erased from existence in a matter of centuries or millennia. Venus, orbiting at 0.72 astronomical units, or 108 million kilometers, faces a similar fate. Most models predict that the Sun's radius will reach or exceed Venus's orbit. Even if the photosphere does not quite reach Venus, the planet will be subjected to such intense heat and radiation that its surface will be completely melted. The already hellish conditions on Venus, where surface temperatures currently hover around 460 degrees Celsius, will worsen beyond imagination. The planet will likely spiral inward due to atmospheric drag and tidal interactions with the Sun's extended envelope, eventually suffering the same fate as Mercury. Earth's fate is less certain and more hotly debated. Earth orbits at 1 astronomical units, or 150 million kilometers from the Sun. If the Sun expands to exactly 1 astronomical units, Earth will be at the very edge of the photosphere, barely skimming the surface of the red giant. But whether Earth is engulfed depends on several factors, including how much mass the Sun loses during the red giant phase and how that mass loss affects Earth's orbit. Stars like the Sun lose a significant fraction of their mass as they evolve off the main sequence and onto the red giant branch. The stellar wind, which is currently weak, becomes much stronger as the star expands and cools. Mass loss rates can increase from the current 10 to the negative 14 solar masses per year to 10 to the negative 8 or even 10 to the negative 7 solar masses per year during the red giant phase. Over the course of a few 100 million years, the Sun could lose 25 to 30% of its total mass, shedding somewhere between 0.25 and 0.3 solar masses into space. This mass loss has an important consequence for the planets. According to orbital mechanics, when a star loses mass, the orbits of its planets expand outward. The less massive the star, the weaker its gravitational pull, and the farther out the planets drift. Earth's orbit could expand to perhaps 1.2 or even 1.5 astronomical units as the Sun loses mass. If the expansion is enough, Earth might just barely avoid being engulfed by the photosphere. But even if Earth survives the initial expansion, it will not survive unscathed. The surface of the Earth will be subjected to temperatures of several thousand degrees Celsius. The oceans, which will have boiled away billions of years earlier during the Great Brightening, will be long gone. The atmosphere, stripped away by the intense radiation and stellar wind, will have vanished. The surface will be molten, a sea of liquid rock glowing red-hot under the bloated sun. The crust will melt. The mantle will convect violently. The planet will become a ball of lava, a miniature version of the young Earth during the Hadean Eon, but with no hope of cooling and solidifying again. If any part of Earth's core remains solid, it will not remain so for long. Even if Earth's orbit expands enough to avoid direct engulfment, there is another danger: tidal interactions. The Sun's extended atmosphere, though tenuous, is not a vacuum. It exerts drag on anything moving through it. Earth, plowing through the outer layers of the red giant, will experience friction that will slowly decay its orbit. The planet will spiral inward, moving ever closer to the denser, hotter regions of the Sun. This is the same process that doomed Mercury and Venus. Once Earth enters the Sun's atmosphere, even at the very edge, its fate is sealed. It will spiral inward over thousands or tens of thousands of years, gradually descending into the inferno until it is finally consumed. Recent observations have provided tantalizing clues about Earth's fate. Astronomers have discovered planets orbiting other stars that appear to have survived their host star's red giant phases. In 2024, a planet roughly the size of Earth was found orbiting a white dwarf, the remnant core left behind after a star sheds its outer layers. The planet's orbit suggests it survived the red giant expansion, either by being far enough away initially or by having its orbit expanded by the star's mass loss. This discovery has sparked debate. If some planets can survive, perhaps Earth can too, but the conditions must be just right, and for Earth, the margin of error is razor-thin. The most likely scenario, according to current models, is that Earth will be engulfed and destroyed. The combination of the Sun's expansion, the drag from the extended atmosphere, and tidal forces will overcome the outward migration caused by mass loss. Earth will spiral inward and be vaporized. The atoms that once made up continents and oceans, mountains and valleys will be dispersed into the Sun's atmosphere, becoming part of the stellar wind that flows out into space. The planet that gave birth to life, that hosted billions of years of evolution, that produced intelligence and civilization, will be reduced to a diffuse cloud of gas, indistinguishable from the rest of the red giant's envelope. But the Sun is not finished. The red giant phase is not the final chapter. Deep inside the collapsing core, something extraordinary is about to happen. The helium ash, the inert remnant of billions of years of hydrogen burning, is piling up, growing denser and hotter. The core is on a countdown to the most violent event in the Sun's life, an event so sudden and so powerful that it will release more energy in a few minutes than the Sun has produced in the last million years. The helium flash is coming, and it will change the Sun once again. Chapter 13: The Helium Flash, the Invisible Explosion. While the outer layers of the Sun swell into a red giant, something strange and dangerous is happening in the core. The helium ash left behind by billions of years of hydrogen burning has been accumulating, growing denser and denser as gravity crushes it inward. The core is no longer fusing anything. It is inert, supported not by the outward pressure of fusion, but by a quantum mechanical effect called electron degeneracy pressure. Degeneracy pressure is one of the strangest predictions of quantum mechanics, and it is the only thing preventing the sun's core from collapsing into oblivion. Normally, the pressure in a gas is determined by temperature. The hotter the gas, the faster the particles move, and the more pressure they exert. But in the core of the sun, the helium has been compressed to such extreme densities that the electrons are packed so tightly together that they enter a regime governed by the Pauli exclusion principle. This principle states that no two electrons can occupy the same quantum state simultaneously. When the density is high enough, all the low-energy quantum states are filled, and the electrons are forced into higher and higher energy states, even though the temperature might not be rising. This creates a pressure that depends only on density, not on temperature. This is electron degeneracy pressure, and it is incredibly strong. It is strong enough to hold up the core against the crushing weight of the overlying layers, but it has a peculiar and dangerous property. It does not respond to temperature changes. In a normal gas, if you heat it up, it expands, which reduces the pressure and stabilizes the system. In a degenerate gas, heating it up does not cause it to expand. The pressure remains almost constant because it depends on density, not temperature. This breaks the normal thermostat that regulates fusion in stars, and it sets the stage for a runaway nuclear reaction. As the hydrogen shell above the core continues to burn, it deposits more and more helium onto the core. The core grows more massive and more compressed. The density increases, and so does the temperature, but the core does not expand because it is supported by degeneracy pressure, not thermal pressure. The temperature rises and rises, climbing from a few million degrees to tens of millions of degrees. Eventually, about 100 million years after the sun first became a red giant, the core temperature crosses a critical threshold, 100 million degrees Celsius. At this temperature, helium nuclei, also known as alpha particles, begin to fuse. But helium fusion is far more difficult than hydrogen fusion. It requires a three-body collision, an event where three helium nuclei come together simultaneously in the same place. This is called the triple alpha process. The first step is the fusion of two helium nuclei to form beryllium-8. But beryllium-8 is unstable. It decays back into two helium nuclei in about 10 to the negative 16 seconds. However, in the dense, hot core, there are so many helium nuclei flying around that occasionally a third helium nucleus will slam into the beryllium-8 before it decays, fusing to form carbon-12. This process was once thought to be impossible. The probability of three particles colliding at exactly the right moment seemed too low. But in 1952, the astrophysicist Fred Hoyle predicted that carbon-12 must have an excited energy state, a resonance, at exactly the right energy to make the triple alpha process efficient. Without this resonance, carbon would not exist in the universe, and neither would life. Hoyle convinced experimentalists to search for this energy level, and they found it exactly where he predicted. This was one of the greatest triumphs of theoretical astrophysics, and it earned Hoyle lasting fame, though he was controversially denied the Nobel Prize. When helium fusion finally ignites in the sun's core, it does not ignite gently. Because the core is degenerate, the increase in temperature from the fusion reactions does not cause the core to expand and cool. Instead, the temperature rises further, which causes the fusion rate to increase, which raises the temperature even more. The triple alpha process has an extraordinarily steep temperature dependence. The reaction rate is proportional to the temperature to the 30th or even 40th power. A small increase in temperature causes a massive increase in the fusion rate. Within seconds, the fusion rate explodes. This is the helium flash. In a matter of minutes, the core releases as much energy as the entire sun normally produces in 100 million years. It is a thermonuclear detonation of cosmic proportions, an explosion that would vaporize any planet if it occurred on the surface. But it does not occur on the surface. It occurs deep inside the core, buried beneath hundreds of thousands of kilometers of stellar envelope. The energy released by the helium flash is entirely absorbed by the core itself. The massive influx of energy finally breaks the degeneracy. The core heats up so much that thermal pressure begins to dominate over electron degeneracy pressure. The core expands, and as it expands, it cools. The runaway fusion reaction stabilizes. Within a few hours, the helium flash is over, and the sun settles into a new equilibrium. From the outside, an observer watching the sun would see almost nothing. The helium flash is entirely invisible. The surface of the sun might flicker slightly, and the luminosity might change by a small amount, but there would be no dramatic explosion, no visible fireworks. The energy is trapped deep inside, and by the time it diffuses outward to the surface, it has been absorbed and re-radiated so many times that the violent event in the core is completely masked. The sun simply transitions from one state to another, and the outside world is none the wiser. After the helium flash, the sun enters a new phase of its life called the horizontal branch. The core is now fusing helium into carbon and oxygen through the triple alpha process, and a shell of hydrogen is still burning around the core. The sun is generating energy from two sources simultaneously. The helium burning in the core is stable, governed by thermal pressure, not degeneracy pressure. The fusion rate adjusts automatically to match the energy needs of the star. The sun contracts slightly from its maximum red giant size, and the surface temperature increases somewhat, though it remains cooler than the main sequence sun. The horizontal branch phase lasts for about 100 million years, a relatively brief period compared to the 10 billion years the sun spent on the main sequence. During this time, the sun is relatively stable, fusing helium in the core and hydrogen in a shell. But this stability is temporary. The helium in the core is being consumed, just as the hydrogen was consumed billions of years earlier. The triple alpha process converts helium into carbon and oxygen, and these elements accumulate as inert ash in the center of the core. The helium fuel will eventually run out, and when it does, the sun will face another crisis, another collapse, and another dramatic transformation. The next phase is the asymptotic giant branch, and it will be the sun's last gasp before death. Chapter 14, The Last Gasp, Thermal Pulses and the AGB Phase. After the relative calm of the horizontal branch, where the sun fuses helium in its core and hydrogen in a shell, the helium fuel in the core begins to run out. The core has been converting helium into carbon and oxygen for about 100 million years, and now the helium is depleted. The core, now composed of inert carbon and oxygen, begins to contract once again under gravity. The temperature rises, but it is not high enough to ignite carbon fusion. Stars like the sun simply do not have enough mass to compress their cores to the temperatures required for carbon burning, which would need around 600 million degrees Celsius. The core becomes inert once more, supported only by electron degeneracy pressure. But above the inert carbon-oxygen core, helium fusion continues in a thin shell, and above that, hydrogen fusion continues in an even thinner shell. The sun is now generating energy from two concentric shells of fusion, one burning helium and one burning hydrogen, with an inert core beneath and a vast, bloated envelope above. This is the asymptotic giant branch, or AGB phase, and it is the final chapter in the sun's active life. The name asymptotic comes from the fact that, on a Hertzsprung-Russell diagram, which plots stars by luminosity and temperature, the AGB track approaches, or asymptotes, the same region of the diagram as the earlier red giant branch. The sun becomes a giant once again, swelling to enormous size, with luminosities reaching thousands of times its main sequence value. But unlike the earlier red giant phase, the AGB phase is unstable, chaotic, and punctuated by violent eruptions called thermal pulses. Thermal pulses are episodic, explosive ignitions of the helium shell. The mechanism works like this. As the hydrogen shell burns, it deposits fresh helium onto the helium shell below. The helium shell becomes thinner and thinner, and the temperature and pressure at its base increase. Eventually, the conditions become right for helium fusion to reignite, but because the shell is so thin and the underlying layers are partially degenerate, the ignition is not gentle, it is explosive. The helium shell flash during a thermal pulse releases enormous amounts of energy, sometimes thousands or even tens of thousands of times the sun's normal luminosity. The energy output can rival the power of a shell flash itself, generating more than 100,000 times the sun's current luminosity for a brief period, though the energy is trapped inside the star and not visible from the outside. The sudden release of energy causes the star to expand dramatically, and the outer layers cool. The expansion shuts off the hydrogen shell above, extinguishing hydrogen fusion temporarily. The energy from the helium flash also drives convection in the region between the helium shell and the hydrogen shell, a zone called the intershell region. This convective zone, called the pulse-driven convection zone, mixes material throughout the intershell, homogenizing the composition. Carbon, produced by the helium fusion during the pulse, is mixed throughout the intershell, along with other elements like oxygen and nitrogen. After a few years, the helium shell flash subsides, the shell cools and contracts, and hydrogen fusion reignites in the shell above. The star settles into a quiescent phase, called the interpulse period, that lasts anywhere from 10,000 to 100,000 years. Then the cycle repeats. The hydrogen shell deposits more helium onto the helium shell. The helium shell thins and heats. Another flash occurs, another pulse. Over the course of the AGB phase, the sun will experience dozens, perhaps hundreds, of these thermal pulses, each one driving the star closer to their end. But the thermal pulses do more than just make the star unstable. They also change the surface composition of the star through a process called the third dredge-up. After a thermal pulse, when the helium shell has cooled and the hydrogen shell has reignited, the base of the convective envelope, the outer layer of the star that extends all the way to the surface, can move inward in mass, penetrating into the intershell region. When this happens, the convective envelope mixes carbon-rich material from the intershell up to the surface. The surface of the sun, which has been hydrogen and helium-rich for its entire life, becomes enriched with carbon. If the third dredge-up is efficient enough, the carbon-to-oxygen ratio at the surface can exceed 1, transforming the sun into a carbon star. Carbon stars are red giants whose atmospheres contain more carbon than oxygen. In a normal oxygen-rich star like the sun, oxygen binds with carbon to form carbon monoxide, and any remaining oxygen forms oxides and silicates. But in a carbon star, there is so much carbon that it cannot all be bound by oxygen. The excess carbon forms molecules like carbon-carbon bonds, graphite, and even soot, giving the star a reddish or sooty appearance. Carbon stars are important for the chemical evolution of the galaxy because they eject carbon-rich dust into the interstellar medium, dust that will eventually be incorporated into new stars and planets. The third dredge-up also brings heavy elements to the surface, elements created by the slow neutron capture process, or S process, which occurs in the helium-burning shell during thermal pulses. The S process builds up heavy elements like barium, strontium, yttrium, and lead by gradually adding neutrons to iron peak elements. These heavy elements, mixed to the surface by the third dredge-up, enrich the interstellar medium when the star eventually ejects its outer layers. AGB stars are one of the primary sources of S-process elements in the galaxy. The AGB phase is also characterized by intense mass loss. The stellar wind, which was already strong during the red giant phase, becomes even more powerful during the AGB phase. Mass loss rates can reach 10 to the -6 or even 10 to the -5 solar masses per year, stripping away the sun's outer envelope at an alarming rate. The mechanism driving this mass loss is not fully understood, but it is thought to involve a combination of radiation pressure on dust grains forming in the cool, extended atmosphere and pulsations in the stellar envelope caused by the thermal pulses. As the dust forms, it absorbs radiation from the star and is pushed outward by radiation pressure. The outward moving dust drags the gas along with it, creating a wind. The wind is so strong that it carries away the entire hydrogen envelope over the course of a few 100,000 years, the duration of the AGB phase. By the end of the AGB phase, the sun will have lost 40 to 50% of its total mass, ejecting more than half a solar mass of material into space. This material forms a slowly expanding shell of gas and dust around the dying star, a shell that will soon become illuminated and transformed into one of the most beautiful objects in the universe, a planetary nebula. The thermal pulses become stronger and more frequent as the AGB phase progresses. The carbon-oxygen core continues to contract and heat even though it is not fusing. The shells above it burn hotter and hotter. Eventually, the mass loss becomes so extreme that the outer envelope is completely stripped away. The hydrogen shell is extinguished. The helium shell flickers out. What remains is the exposed core, a tiny, incredibly hot object about the size of the Earth, but with half the mass of the Sun. This is a white dwarf, and it is the corpse of the Sun, the final resting state for a star that has consumed all its fuel and expelled all its outer layers. But the story is not over yet. The ejected material, now drifting outward into space, is about to be transformed. Chapter 15: The Planetary Nebula and the White Dwarf. The Sun is dead. The fusion has stopped. The outer envelope has been stripped away by the relentless stellar wind. All that remains is the naked core, a white dwarf, a crystalline sphere of carbon and oxygen about the size of Earth, glowing white-hot with a surface temperature of 100,000 degrees Celsius or more. The white dwarf is not generating energy through fusion. It is simply radiating away the residual heat left over from billions of years of nuclear burning, slowly cooling over trillions of years. But before it fades into darkness, the white dwarf will illuminate its surroundings in a final, spectacular display. The material ejected during the AGB phase, the hydrogen and helium-rich envelope that was stripped away by the stellar wind, is now drifting outward into space at speeds of 10 to 30 kilometers per second. This material forms a shell, or sometimes multiple shells, surrounding the white dwarf. For thousands of years, this shell was dark, invisible, illuminated only by the faint light of the dying star. But now, the white dwarf has reached a temperature high enough to emit intense ultraviolet radiation. When the surface temperature exceeds about 30,000 degrees Celsius, the ultraviolet photons streaming out from the white dwarf are energetic enough to ionize the surrounding gas. Ionization is the process of stripping electrons away from atoms. When an ultraviolet photon with enough energy strikes a hydrogen atom, it kicks the electron out of the atom, leaving behind a proton. The free electron can then recombine with another proton, and when it does, it emits a photon of visible light. This is how a planetary nebula shines. It is not hot enough to glow on its own. It is lit up by the ultraviolet radiation from the white dwarf at its center, like a fluorescent light bulb. The result is one of the most beautiful objects in the universe. Planetary nebulae are glowing shells of gas in space, often with intricate symmetrical shapes: spheres, rings, hourglasses, butterflies, and spirals. They glow in brilliant colors: red from hydrogen, green from oxygen, blue from helium. The Ring Nebula, the Helix Nebula, the Cat's Eye Nebula, and the Dumbbell Nebula are all planetary nebulae, the final exhalations of stars like the Sun. The name planetary nebula is a historical misnomer. When these objects were first observed in the 18th century through small telescopes, they appeared as round, fuzzy disks, similar to the appearance of planets. Early astronomers did not realize they were looking at the death throes of stars. They thought they were looking at planets or planetary systems in formation. The name stuck, even after the true nature of these objects was understood. Planetary nebulae are fleeting. They last only a few tens of thousands of years before the expanding shell becomes so diffuse that it fades from view and merges with the interstellar medium. The ultraviolet radiation from the white dwarf, which is what keeps the nebula ionized and glowing, also diminishes over time as the white dwarf cools. After about 50,000 years, the nebula has expanded too far and become too thin to glow brightly. The beautiful colors fade, and the nebula disappears, leaving behind only the white dwarf, alone in the darkness. The white dwarf itself is a strange and extreme object, governed by physics that does not apply to normal matter. It is supported not by thermal pressure, but by electron degeneracy pressure, the same quantum mechanical effect that supported the core during the helium flash. The electrons in the white dwarf are packed so tightly that they are forced into higher and higher energy states by the Pauli exclusion principle. This creates a pressure that is independent of temperature, a pressure that can support the star against gravity even as the star cools and loses thermal energy. A white dwarf is incredibly dense. A teaspoon of white dwarf material would weigh about 5 tons on Earth. The gravity at the surface of a white dwarf is roughly 100,000 times stronger than Earth's gravity. If you could stand on the surface, which you cannot, you would be crushed instantly into a layer of atoms a few nanometers thick. The intense gravity also causes the white dwarf to be very small. Despite having half the mass of the Sun, the white dwarf is only about the size of the Earth, with a radius of roughly 5,000 to 10,000 kilometers. The composition of the white dwarf depends on the history of the star. For a star like the Sun, the white dwarf is made primarily of carbon and oxygen, the products of helium fusion during the horizontal branch and AGB phases. The carbon and oxygen are mixed throughout the core, though there may be some layering, with heavier oxygen sinking toward the center. The white dwarf is covered by a thin layer of helium, left over from the helium shell, and an even thinner layer of hydrogen, the last remnant of the hydrogen. As the white dwarf cools, something extraordinary happens in its interior. At a certain temperature, roughly 10 million degrees Celsius, the ions in the core begin to crystallize. In the hot, dense interior of the white dwarf, the carbon and oxygen ions, which have been moving freely in a plasma, slow down as the temperature drops. Eventually, the electrostatic forces between the ions become strong enough to overcome the thermal motion, and the ions lock into a crystalline lattice structure. The white dwarf becomes a giant, stellar mass diamond, shining faintly in the darkness. The crystallization process releases energy in the form of latent heat, which slows the cooling of the white dwarf. This creates a pileup in the white dwarf cooling sequence, where white dwarfs spend a longer time at the temperature where crystallization occurs. Astronomers have observed this pileup in the Hertzsprung-Russell diagram for white dwarfs, confirming that crystallization is really happening. The crystallization also allows for phase separation, where oxygen, being denser, sinks toward the center, displacing the lighter carbon. This sedimentation releases additional gravitational energy, further slowing the cooling. The white dwarf will continue to cool for trillions of years. Its surface temperature will drop from 100,000 degrees to 10,000 degrees, then to 1,000 degrees, and eventually to the temperature of the surrounding space, just a few degrees above absolute zero. At that point, it will no longer glow. It will emit no light, no heat. It will become a black dwarf, a cold, dark, crystalline remnant, invisible against the black background of space. But black dwarfs do not exist yet. The universe is only 13.8 billion years old, far too young for any white dwarf to have cooled completely. The oldest white dwarfs in the galaxy, formed from the first generation of stars, are still glowing faintly, with surface temperatures of a few thousand degrees. Calculations suggest that it will take at least 100 quadrillion years, and possibly much longer, for a white dwarf to cool to the point where it becomes a black dwarf. That is roughly 10,000 times the current age of the universe. By the time the first black dwarfs form, the universe will be a very different place. All the stars will have burned out. Galaxies will have dispersed. The universe will be cold, dark, and empty. The Sun's white dwarf will eventually join the ranks of black dwarfs, drifting through the cosmos as a frozen monument to what once was. But even black dwarfs may not be eternal. Some theoretical models suggest that protons, the building blocks of matter, may be unstable and decay over timescales of 10 to the 32nd power years or longer. If protons decay, then all baryonic matter, including black dwarfs, will eventually evaporate into photons and lighter particles. The universe will end not with a bang, but with a whisper, as the last particles of matter dissolve into radiation and disappear into the void. This is the final chapter, the ultimate fate of the Sun and everything it touched. Chapter 16, The Eternal Corpse, the Black Dwarf. The white dwarf that was once the Sun will cool for an incomprehensible span of time. For the first few million years, it will remain hot, glowing white or blue-white, shining with a luminosity roughly 1/10,000th that of the current Sun. But it is not generating new energy. There is no fusion happening in the core, no shell burning, no nuclear reactions of any kind. The white dwarf is simply radiating away the residual thermal energy left over from billions of years of fusion. It is a dying ember, fading slowly into darkness. As the white dwarf cools, its surface temperature drops. It transitions from white to yellow, then to red, and finally to infrared. After about 1 billion years of cooling, the surface temperature will have dropped to around 5,000 degrees Celsius, roughly the temperature of the sun's photosphere today. After 10 billion years, it will be down to a few thousand degrees. After 100 billion years, it will be cooler than the human body, glowing only faintly in the infrared. And it will keep cooling, asymptotically approaching the temperature of the cosmic microwave background radiation, the faint afterglow of the Big Bang, which currently sits at about 2.7 degrees above absolute zero. Eventually, after a time so long that it defies human comprehension, the white dwarf will stop emitting any detectable radiation. It will become a black dwarf, a cold, dark, crystalline sphere drifting through the void, invisible against the black background of space. The black dwarf will be composed almost entirely of crystallized carbon and oxygen, locked into a diamond-like lattice structure by electron degeneracy pressure. It will be a stellar corpse, a monument to a star that once burned bright, a star that gave life to a planet that produced intelligence and civilization. But all of that will be long, long gone. Black dwarfs do not exist yet. The universe is only 13.8 billion years old. Far too young for any white dwarf to have cooled completely to the point where it no longer emits any radiation. The oldest white dwarfs in the Milky Way, formed from the first generation of stars more than 10 billion years ago, are still glowing faintly with surface temperatures of a few thousand degrees. They are cool white dwarfs, but they are not black dwarfs. Calculations suggest that it will take at least 100 quadrillion years, and possibly much longer, for a white dwarf to cool to the temperature of the surrounding space. That is roughly 10,000 times the current age of the universe. By the time the first black dwarfs form, the cosmos will be unrecognizable. All the stars currently shining in the sky will have burned out. The Milky Way will have long since merged with Andromeda, forming a giant elliptical galaxy. The smaller galaxies in the local group will have been absorbed. The galaxy clusters will have dispersed. Star formation will have ceased, as all the hydrogen gas in the universe will have been either converted into stars or dispersed so thinly that it can no longer collapse to form new stars. The universe will be a graveyard of stellar remnants, white dwarfs, neutron stars, and black holes drifting in the darkness, separated by ever-increasing distances as the expansion of the universe accelerates. The far future of the universe is dominated by the relentless increase of entropy and the gradual decay of all structure. This is the heat death of the universe, a state where all energy has been evenly distributed, where no temperature gradients exist, and where no work can be done. In this ultimate state, the universe reaches maximum entropy. Stars have burned out, black holes have evaporated, matter has decayed. Only a thin soup of photons and elementary particles remains, spread across an ever-expanding void. But recent theoretical work suggests that even black dwarfs may not be eternal. In 2025, physicists calculated that all objects in the universe, including white dwarfs, are subject to a form of quantum evaporation similar to Hawking radiation, the process by which black holes slowly lose mass and eventually evaporate. This Hawking-like radiation applies not just to black holes, but to all objects with gravitational fields. The stronger the gravity, the faster the evaporation. For a white dwarf, the evaporation rate is incredibly slow, but it is not zero. According to these calculations, a white dwarf will completely evaporate in about 10 to the 78th power years. That is a 1 followed by 78 zeros, a timescale so vast that it makes the current age of the universe, a mere 13.8 billion years, seem like the blink of an eye. Previous estimates, which did not take this quantum evaporation into account, suggested that white dwarfs could survive for 10 to the 1100th power years or longer. But with this new understanding, the ultimate fate of white dwarfs, and indeed all matter, is sealed. They will evaporate. They will dissolve into radiation. They will disappear. But there is an even more speculative process that could destroy black dwarfs long before quantum evaporation becomes significant: proton decay. Proton decay is a hypothetical process predicted by some grand unified theories, or guts, which attempt to unify the electromagnetic, weak, and strong nuclear forces into a single fundamental force. These theories suggest that protons, which are currently thought to be stable, may in fact be unstable and will eventually decay into lighter particles like positrons and photons. The predicted lifetime of a proton varies widely depending on the specific gut model, but most estimates fall in the range of 10 to the 31st power to 10 to the 36th power years. Some models push the lifetime even higher, to 10 to the 39th power years or beyond. For comparison, the current age of the universe is only about 10 to the 10th power years. Proton decay, if it occurs, is an extraordinarily slow process, but it is not impossible. Experiments have been searching for proton decay for decades. Giant underground detectors filled with tens of thousands of tons of ultra-pure water, like Superkamiokan in Japan, watch for the telltale flash of light that would signal the decay of a single proton. So far, no proton decay has ever been observed. The current experimental lower limit on the proton lifetime is about 10 to the 34th power years, which has ruled out the simplest and earliest gut models. But many more complex models predict lifetimes well above the current experimental limits, so the possibility of proton decay remains open. If protons do decay, then all baryonic matter, including black dwarfs, neutron stars, and even the atoms in your body, will eventually disintegrate. A black dwarf, composed primarily of carbon and oxygen nuclei, will slowly evaporate as its protons decay one by one. Each decay will release a tiny burst of energy in the form of photons and positrons, which will annihilate with any remaining electrons to produce more photons. Over timescales of 10 to the 32nd power to 10 to the 40th power years, the black dwarf will dissolve into a diffuse cloud of radiation, leaving nothing behind. But even if protons are perfectly stable, even if quantum evaporation is slower than current models predict, the universe will still reach a state of maximum entropy. This is the inevitable consequence of the second law of thermodynamics, which states that the entropy of a closed system always increases over time. The universe, as a whole, is a closed system. It is not exchanging energy with anything outside itself, because there is nothing outside itself. And so, the entropy of the universe must increase, relentlessly, inexorably, until it reaches its maximum possible value. When the universe reaches maximum entropy, it will be in a state of perfect equilibrium. All temperature gradients will have vanished, all chemical reactions will have ceased, all motion will have stopped, except for the random thermal jittering of particles at the background temperature. No stars will shine, no planets will orbit, no life will exist. The universe will be cold, dark, and utterly lifeless. This is the heat death, the final state of the cosmos, the end of all things. But is this truly the end? Some physicists have speculated that, over unimaginably long timescales, quantum fluctuations could spontaneously create pockets of low entropy within the dead universe. These fluctuations could, in theory, lead to the formation of new structures, new particles, even new universes. The Poincaré recurrence theorem suggests that, given infinite time, any system will eventually return to a state arbitrarily close to its initial state. This means that, if we wait long enough, the universe could spontaneously recreate itself, producing another Big Bang, another expansion, another epoch of stars and galaxies and life. But the timescales involved are beyond comprehension. The Poincaré recurrence time for the entire observable universe is estimated to be around 10 to the 10 to the 10 to the 56th power years. That is not a typo. It is a number so large that it cannot be written out, even if every atom in the observable universe were used as a digit. It is a number that makes infinity seem close by comparison. And even if such a recurrence were to occur, there is no guarantee that the new universe would resemble the old one in any way. It could be a universe with different physical laws, different constants of nature, a universe hostile to the formation of stars, planets, and life. The Sun, the star that has defined our existence for 4.6 billion years, will end its life as a white dwarf, cooling slowly into a black dwarf, and eventually, on timescales beyond imagination, evaporating into nothingness. The planets, if any survive the red giant phase, will drift in the darkness, frozen, lifeless, orbiting a dead star until gravitational perturbations eject them into interstellar space, or they fall into the white dwarf. The solar system, as a coherent structure, will dissolve, its components scattered across the galaxy. But even in death, the sun will leave a legacy. The material it ejects during the AGB phase, enriched with carbon, nitrogen, oxygen, and heavy elements forged in its core and shells, will merge with the interstellar medium. This enriched gas will eventually collapse to form new stars, new planets, and perhaps new life. The atoms that once made up the sun will be recycled, incorporated into future generations of stars. The carbon in your body, the oxygen you breathe, the iron in your blood, were all forged in the cores of stars like the sun, stars that lived, died, and returned their ashes to the cosmos. We are made of star stuff, as Carl Sagan famously said, and when we die, our atoms will return to the stars. This is the great cosmic cycle, the endless recycling of matter and energy, the rise and fall of structure in an expanding universe. The sun is one small part of this cycle, a single star among hundreds of billions in the Milky Way, one of hundreds of billions of galaxies in the observable universe. Its story is remarkable, but it is not unique. Every star goes through a similar journey, from birth in a molecular cloud to death as a white dwarf, neutron star, or black hole. And every star, in its own way, contributes to the evolution of the cosmos, enriching the interstellar medium, seeding the formation of new stars and planets, and making possible the emergence of complexity, life, and intelligence. Chapter 17: Reflection and Legacy. We have reached the end of the sun's story, and with it, the end of this first chapter in our exploration of the solar system. Over the course of this journey, we have witnessed the birth of the sun in violence and chaos, triggered by the death of a nearby massive star. We have descended into the core, where quantum tunneling makes the impossible routine, and where 4 million tons of matter are converted into pure energy every second. We have traced the 100,000-year journey of a single photon as it fought its way from the crushing depths of the radiative zone to the boiling surface of the convective zone. We have explored the tachocline, the mysterious boundary layer where the sun's magnetic dynamo operates, and we have witnessed the fury of solar flares and coronal mass ejections, events capable of crippling modern civilization. We have looked forward to the distant future, a billion years from now, when the sun's increasing brightness will boil the oceans off the Earth and sterilize the biosphere. We have seen the sun swell into a red giant, consuming Mercury and Venus, and possibly Earth, in its bloated, dying envelope. We have witnessed the helium flash, a thermonuclear detonation deep in the core that releases a galaxy's worth of energy in minutes, but is invisible from the outside. We have watched the sun pulsate and eject its outer layers during the asymptotic giant branch phase, creating a planetary nebula, one of the most beautiful objects in the universe. And we have followed the sun's final remnant, a white dwarf, as it cools over trillions of years into a black dwarf and eventually evaporates into nothingness. This is the complete story of our sun, from its violent birth 4.6 billion years ago to its cold, dark death trillions of years in the future. It is a story of creation and destruction, of stability and chaos, of life and death. The sun has been our constant companion throughout the history of humanity. It has warmed our planet, powered the biosphere, and made life possible. It has been worshipped as a god, studied by scientists, and feared as a harbinger of doom. It is the most important object in our sky, the center of our solar system, the anchor that holds the planets in their orbits. But the sun is not eternal. It is a star, and stars are born, they live, and they die. The sun's death is inevitable, written into the laws of physics, dictated by the finite supply of hydrogen fuel in its core. Long before the sun becomes a red giant and swallows the inner planets, it will have already killed the Earth by simply growing too bright. The biosphere has perhaps a billion years left, maybe less. Complex life will vanish. The oceans will boil away. The planet will become a barren, scorched wasteland, and billions of years after that, the sun itself will fade into darkness, leaving behind only a cold, crystalline corpse. This timeline is incomprehensibly long from a human perspective. A billion years is 200,000 times longer than the entirety of human civilization. It is 200 million times longer than a human lifetime. On these timescales, continents drift across the globe, mountain ranges rise and erode, entire species evolve and go extinct. The future extinction of life on Earth, caused by the brightening of the sun, is so far away that it seems almost meaningless to us. But it is coming. It is as certain as the sunrise. What does this mean for us, for humanity, for our brief flicker of consciousness in the vastness of cosmic time? The existential philosophers have long grappled with the tension between the finite and the infinite, between the transience of human life and the apparent permanence of the universe. We are born, we live for a handful of decades, and we die. Our individual existence is fleeting, a single frame in a film that has been running for billions of years and will continue for trillions more. In the face of such vastness, it is easy to feel insignificant, to wonder if anything we do matters, if our struggles and achievements have any meaning at all. But there is another way to see it. The sun's story is also our story. We are made from the ashes of stars that died long before the sun was born. The carbon in our cells, the calcium in our bones, the iron in our blood, were all forged in the nuclear furnaces of massive stars that exploded as supernovae and scattered their enriched material across the galaxy. We are quite literally the universe experiencing itself. We are the sun's children, born from its light, sustained by its warmth, and destined to perish when it grows too bright. Our existence is improbable. The chain of events that led from the Big Bang to the formation of the Milky Way, from the collapse of a molecular cloud to the ignition of the sun, from the accretion of planetesimals to the formation of Earth, from the emergence of life to the evolution of intelligence, is so unlikely, so dependent on precise conditions and fortunate coincidences that it borders on the miraculous. And yet, here we are. Conscious, self-aware, capable of understanding the universe, of tracing the history of the sun, of predicting its future, and of contemplating our own mortality. The transience of our existence does not diminish its value. If anything, it makes it more precious. We have a brief moment in the sun's light, a few billion years at most, to explore, to learn, to create, to love, to find meaning in a universe that does not provide it for us. The universe is indifferent to our existence, but we are not indifferent to the universe. We care, we wonder, we ask questions, we seek answers. And in doing so, we give meaning to the cosmos, even if only for ourselves, even if only for a fleeting moment. This concludes our exploration of the sun. It is the first body in our solar system tour, but it is the most important, for without it, nothing else would exist. In future chapters, we will explore the planets, moons, asteroids, and comets that orbit this dying star. We will walk on the surfaces of alien worlds, dive into the atmospheres of gas giants, and investigate the icy bodies at the edge of the solar system. Each world has its own story, its own history, its own mysteries, but all of them, every single one, owe their existence to the sun. Before we move on, remember this. Every time you feel the warmth of the sun on your skin, you are feeling the light from a fusion reaction that began tens of thousands of years ago, deep in the core, and only just now escaped. You are connected to the sun, to the stars, to the cosmos itself. You are made of star stuff. And one day when you die, your atoms will return to the universe to be recycled into new stars, new planets, and perhaps new life. If you enjoyed this journey through the complete story of the sun, hit that like button and subscribe for the next episode, where we will begin our exploration of the planets. The solar system awaits, and we are just getting started.